Hello there, and welcome back to the channel, where we explore the mysteries hiding in the darkness between the stars. Tonight, we're diving into something that has astronomers around the world scratching their heads and questioning everything they thought they knew about the cosmos. On July 1st, 2025, a routine sky survey spotted something extraordinary hurtling through our solar system. And what started as just another dot of light has become one of the most puzzling objects ever detected from interstellar space. Before we unpack this cosmic mystery, I'd love to know where in the world you're watching from and what drew you to this particular corner of the universe tonight. If you find these deep dives into astronomical anomalies as fascinating as I do, I'd be incredibly grateful if you hit that like button and maybe even subscribe. It helps these explorations reach other curious minds who might be wondering about the same strange signals we're about to discuss. Avi Loeb recently discussed new spectroscopic data from the Very Large Telescope, VLT in Chile, showing unusually high nickel production by 3I/Atlas. The observations were made via the UVES spectrograph, measuring the abundances of nickel and iron in the gas plume around 3I/Atlas at various distances from the Sun, from about 3.14 astronomical units down to 2.14 astronomical units. Key findings include nickel is detected consistently even at greater heliocentric distances, whereas iron is only seen when 3I/ATLAS approaches closer than 2.64 astronomical units. The ratio of nickel to iron is far higher than what is typical for solar system comets, or even for 2I/Borisov, making 3I/Atlas exceptional in its chemical signature. This is puzzling because at those cold distances, temperatures are usually too low to vaporize metals such as nickel or iron from their host grains. So the presence of these metals in the coma is unexpected. Based on images and orbital data, Loeb estimates 3I/ATLAS may exceed 5 kilometers in diameter, making it much more massive than earlier interstellar objects like Oumuamua. Upcoming planetary missions, NASA's Mars Reconnaissance Orbiter and ESA's Mars Orbiters, are planned to observe 3I/ATLAS as it passes relatively close to Mars, giving opportunities for high-resolution imaging. Loeb emphasizes the challenge: the extreme nickel/iron ratio and behavior defy easy classification. Although he leans toward a natural comet explanation, he admits we must remain open to black swan possibilities, that 3I/ATLAS could be something quite extraordinary. Now let's dig into the backstory of 3I/Atlas so we can understand a full picture of why this nickel matters. Now I should warn you, this story gets more peculiar with every new observation, and by the end you might find yourself questioning whether we're looking at the most exotic natural chemistry ever discovered, or something even more extraordinary. So settle in, take a deep breath, and let's begin our journey into the enigma that is 3I/Atlas. When the Asteroid Terrestrial Impact Last Alert System telescope in Rio Hurtado, Chile, first captured images of this visitor on that summer morning in 2025, the astronomers initially thought they were looking at just another space rock, perhaps an asteroid that had wandered a bit too far from its usual neighborhood. But as they tracked its trajectory, something became immediately clear. This object was moving far too fast to be bound by our sun's gravity. The mathematics were unmistakable. 3I/Atlas, as it came to be designated, was following what astronomers call a hyperbolic trajectory. Imagine throwing a ball so hard that it never comes back down. That's essentially what this object was doing on a cosmic scale. It had arrived from the vast emptiness between the stars traveled through our solar system, and would continue its journey into the infinite darkness beyond, never to return. This designation 3I holds profound significance in astronomical history. It marks this as only the third confirmed interstellar object ever detected. Visiting our solar system, the first was the now famous Oumuamua discovered in 2017, a mysterious elongated object that sparked years of debate about its unusual properties. Then came 2I/Borisov in 2019. a more conventional-looking comet that seemed to behave much like the icy visitors we know from our own solar system. But 3. I Atlas from the very beginning seemed different. The timing of its discovery was remarkably fortunate. Detected several months before its closest approach to the Sun, it offered astronomers an unprecedented opportunity to study an interstellar visitor in detail. Most such objects are discovered only after they've already rounded the Sun and begun their journey back to deep space, leaving little time for comprehensive observation. As word spread through the global astronomical community, telescopes around the world began turning their attention to this cosmic wanderer. What they found would challenge fundamental assumptions about the chemistry of space objects and open up questions that reach to the very heart of how we understand the universe. The first hints that 3I Atlas was no ordinary visitor came from spectroscopic observations conducted by the Very Large Telescope in Chile on July 20th, 2025. Spectroscopy is essentially the art of breaking starlight into its component colors, much like a prism splits white light into a rainbow. But instead of creating pretty patterns, these instruments reveal the chemical fingerprints of distant objects. When astronomers pointed their spectrographs at 3I Atlas, they expected to see the usual signatures of a comet, water vapor, carbon dioxide, perhaps some organic compounds sublimating from the icy nucleus as it warmed in the Sun's embrace. What they found instead was something that had never been observed in 4 decades of studying comets and asteroids. Blazing through the darkness around 3I Atlas was the unmistakable signature of atomic nickel, 22 distinct spectral lines, creating a characteristic glow as metal atoms fluoresced under solar radiation. Each line corresponded to specific electronic transitions in nickel atoms, creating a fingerprint that could not be mistaken for any other element. Now you might think, well, nickel in space, that's not so unusual. After all, we know that heavy metals are forged in the hearts of dying stars and scattered throughout the cosmos when those stars explode as supernovas. And you'd be right. Nickel emission has been detected in other comets, including the previous interstellar visitor 2, I Borisov. But here's where 3I Atlas begins to shatter our expectations. When astronomers looked for the spectral lines of iron, which should accompany nickel in any natural cosmic process, they found nothing. No iron emission at all. This absence wasn't subtle. It was complete, and it was unprecedented in the grand story of cosmic chemistry. Nickel and iron are like inseparable twins forged together in stellar cores during the same nuclear fusion processes, scattered together by the same supernova explosions, incorporated together into the same asteroids, comets, and planetary systems for over 4 billion years of studying space objects. This pairing has been as reliable as sunrise. The cosmic abundance of these elements reflects billions of years of stellar evolution. Iron makes up about 32 parts per million of the universe, while nickel comprises about 58 parts per billion. They're created through identical nucleosynthesis processes in massive stars and expelled together when those stars die violently in supernova explosions. When you examine meteorites that fall to Earth, you find nickel and iron together. When you study the spectral lines of distant stars, you see nickel and iron together. When you analyze the chemical composition of asteroids, comets, and planetary atmospheres, you find these elements in predictable ratios reflecting their cosmic heritage until 3I Atlas. The detection of nickel without iron doesn't just break a trend, it shatters a fundamental rule of cosmic chemistry that has held true across every environment we've ever studied, from the cores of planets to the atmospheres of distant exoplanets. This violation represents either the discovery of entirely unknown natural processes or evidence of something far more extraordinary. As July turned to August and 3I Atlas continued its approach toward the Sun, the observations became even more perplexing. The Very Large Telescope detected not only the continuing nickel emission, but also the signature of cyanide molecules streaming from the object's nucleus. The production rates were staggering at a distance of 2.85 astronomical units from the Sun, roughly 427 million kilometers. 3I Atlas was ejecting approximately 5 grams of pure nickel every second. To put this in perspective, that means this mysterious visitor was vaporizing over 430 kilograms of nickel every single day, while simultaneously releasing more than 1,700 kilograms of cyanide. But perhaps most remarkable was how dramatically these emission rates increased as the object approached the Sun in typical comets. The outgassing of material follows predictable patterns as solar heating warms the nucleus, ice sublimates, and carries dust and gas away from the surface. The rate of this process increases with proximity to the Sun, but usually following gentle curves that astronomers can model and predict. 3. I-Atlas defied these expectations entirely. The nickel emission increased following a power law relationship so steep that it was unlike anything ever observed. The mathematical expression showed the emission rate varying with heliocentric distance to the power of -8.43, meaning that as the object moved closer to the Sun, the nickel production didn't just increase, it exploded exponentially. This exponential behavior suggested physical processes fundamentally different from normal cometary activity. It was as if 3I Atlas contained materials or mechanisms that responded to solar heating in ways that had never been documented in our solar system's native comets. Meanwhile, the James Webb Space Telescope turned its unprecedented infrared capabilities toward this enigmatic visitor on August 6, 2025. Webb's near-infrared spectrograph captured detailed spectra across wavelengths from 0.6 to 5.3 micrometers, revealing a chemical composition that added yet another layer to the mystery. The dominant component in 3I Atlas's coma wasn't water vapor as expected in most comets, but carbon dioxide. The mixing ratio of carbon dioxide to water was measured at 8:1, making this one of the most carbon dioxide-rich objects ever studied. This extreme composition placed 3I Atlas in a category shared by only one other known comet, the peculiar Oort cloud visitor, 2016 R2. This carbon dioxide dominance is particularly puzzling because water ice is typically the most abundant volatile component in comets from our solar system. The fact that 3I Atlas breaks this fundamental pattern suggests either an origin in a very different stellar environment or formation processes, unlike anything that occurred in our own solar nebula. Webb also detected water vapor, carbon monoxide, carbonyl sulfide, and various dust components, creating a chemical portrait of an object. Unlike any previously studied, the detection of carbonyl sulfide was particularly intriguing, as this molecule is relatively rare in cometary environments and could provide clues about exotic chemical processes occurring within the object. But it was the temporal evolution of the metal emissions that truly captured scientists' attention. New observations spanning 6 time periods, from August through September, revealed that while nickel was detected throughout the entire observation campaign, iron only appeared when 3I Atlas was closer than 2.64 astronomical units to the Sun. This temporal separation of nickel and iron emission suggested that whatever processes were releasing these metals operated through fundamentally different mechanisms. The fact that iron required closer solar distances to appear, while nickel streamed freely from greater distances, implied either different sublimation temperatures for the host materials or entirely separate chemical pathways for their release. The precision of these measurements was remarkable, with error bars of just a few percent, demonstrating the exceptional quality of the observations and the confidence scientists had in these unprecedented findings. The production rates indicated an incredibly active object that was outgassing substantial amounts of material. As it approached the Sun by late August, deep imaging by the Gemini South Telescope revealed that 3I Atlas had developed a classical cometary tail about 56,400 kilometers long, pointing away from the Sun. The coma had expanded to nearly 19,000 kilometers in diameter, significantly larger than its compact appearance in early July. This morphological evolution provided visual confirmation of the object's increasing activity as it approached the Sun. The teardrop shape was characteristic of dust and gas being swept away by solar radiation pressure, and the solar eye atlas was behaving like a conventional wind, indicating that despite its anomalous chemistry, 3 comet, in terms of its overall structure, yet questions about its size remained tantalizingly unanswered. Hubble Space Telescope observations suggested a nucleus diameter somewhere between 440 meters and 5.6 kilometers. But more precise measurements would require closer observation. The statistical improbability of detecting such a large interstellar object has raised fundamental questions about our understanding of the population of visitors from beyond our solar system. If objects like 3I Atlas are as rare as current models suggest, we should have detected thousands of smaller interstellar visitors before encountering one of this massive scale. The mystery deepens when we consider the proposed explanations for 3I Atlas's extraordinary nickel signature. Some researchers have suggested that the answer might lie in exotic organometallic compounds, particularly nickel tetracarbonyl, a fascinating molecule that could explain some of the anomalous observations. Nickel tetracarbonyl is a compound known from industrial chemistry where nickel atoms bond with carbon monoxide molecules, creating a structure that's both highly volatile and remarkably unstable. This molecule has the peculiar property of decomposing readily under ultraviolet radiation, breaking apart to release pure nickel vapor and carbon monoxide gas in the harsh environment of space, where ultraviolet radiation from stars bathes every surface. Nickel tetracarbonyl would indeed break down rapidly, releasing streams of atomic nickel while leaving behind gaseous carbon monoxide. This process could potentially account for the abundant carbon monoxide detected by Webb's observations, while explaining the pure nickel emission that has baffled astronomers. But here's where this explanation becomes both intriguing and troubling. Nickel tetracarbonyl represents a type of chemistry that's essentially unknown in natural cosmic environments. While we routinely encounter carbon monoxide and nickel separately in space, the specific conditions required to form and preserve nickel tetracarbonyl compounds are not found in typical stellar or planetary environments. The formation of such organometallic compounds would require a precise combination of temperatures, pressures, and chemical conditions that don't exist in the cold vacuum of interstellar space, or in the typical environments where comets form around young stars. This presents a fundamental puzzle. If 3I Atlas contains nickel tetracarbonyl, where and how did such exotic chemistry originate? Some scientists have proposed that these compounds might form through previously unknown processes involving space weathering, the bombardment of surfaces by cosmic rays and solar wind over millions of years. Perhaps these high-energy particles could somehow catalyze the formation of organometallic compounds from more conventional starting materials. Yet even these proposed mechanisms require conditions and processes that remain largely theoretical. No laboratory experiments have successfully demonstrated the formation of stable nickel tetracarbonyl compounds under conditions that mimic the interstellar environment. The gap between what we observe in 3I Atlas and what we can explain through known natural processes continues to widen. This brings us to one of the most unsettling aspects of the 3I Atlas mystery: the industrial connection on Earth. The separation of nickel from iron is routine in manufacturing. Advanced alloys, specialized electronics, and aerospace technology often require purified nickel for specific properties like radiation, resistance, corrosion, immunity, or particular magnetic characteristics. The MON process used in terrestrial industry specifically employs nickel carbonyl as an intermediate compound to produce ultra-pure nickel metal. This industrial pathway routinely creates nickel without iron, exactly matching the chemical signature observed streaming from 3I Atlas. The parallel is so precise that it's difficult to ignore. Modern aerospace applications frequently require nickel alloys with precisely controlled compositions, often with minimal iron content to achieve specific thermal, magnetic, or structural properties. These manufacturing processes represent sophisticated metallurgical techniques that can selectively extract and purify metals to extraordinary degrees of purity. The fact that such purification processes are commonplace in human technology, but unknown in natural cosmic environments, has led some researchers to ask uncomfortable questions about the true nature of 3I Atlas. Are we observing the first confirmed example of exotic natural chemistry, unlike anything in our solar system? Or might we be witnessing evidence of processes that extend beyond the natural world? Prominent astrophysicist Avi Loeb has been particularly vocal about these possibilities, noting that the detection of nickel without iron is only known to exist in industrially produced alloys made through artificial chemical pathways. Loeb's analysis points out that the combination of anomalous properties observed in 3I Atlas creates a compelling case for considering explanations beyond conventional cometary science. The statistical argument adds another layer of complexity to this mystery. The detection sequence of interstellar objects presents a puzzle that challenges our understanding of what should be out there. Oumuamua, the first confirmed interstellar visitor, was roughly the size of a football field with dimensions of about 100 meters. 2I Borisov. The second visitor was somewhat larger, but still relatively modest in scale. Then came 3I Atlas, potentially over 5 kilometers in diameter, making it roughly 1,000,000 times more massive than Oumuamua. This dramatic size progression doesn't match what models predict for interstellar object populations. If large objects like 3I Atlas are as rare as current theories suggest, we should have detected thousands of smaller interstellar visitors before encountering something of this scale. The fact that we've observed the reverse pattern, larger objects appearing more frequently than smaller ones, suggests either our models are fundamentally flawed, or 3I Atlas represents something more unusual than a random cosmic wanderer. The upcoming observations promise to shed new light on these mysteries between October 1st and 7th, 2025. 3I Atlas will pass within 29 million kilometers of Mars, providing an unprecedented opportunity for detailed study NASA's Mars Reconnaissance Orbiter, along with European Space Agency missions. Mars Express and ExoMars will turn their instruments toward this enigmatic visitor. The HiRISE camera aboard the Mars Reconnaissance Orbiter will obtain images with exceptional spatial resolution of 30 kilometers per pixel, potentially revealing surface features, rotation, characteristics, and the true extent of the nucleus versus its surrounding coma. These observations could definitively determine whether the object's brightness comes from a genuinely massive nucleus or from an unusually dense and reflective cloud of material. Even more ambitious is NASA's proposed plan to redirect the Juno spacecraft, currently orbiting Jupiter, for a close encounter with 3I Atlas. The mission would require a critical trajectory change in mid-September 2025, using a gravity assist near Jupiter to send Juno toward a flyby in March 2026, potentially bringing the spacecraft within 25 million kilometers of the mysterious object. Such a close encounter would represent humanity's first dedicated spacecraft mission to an interstellar object. Juno's suite of scientific instruments could analyze the unique chemical signatures that have made 3I Atlas so puzzling. The spacecraft's magnetometer could detect any magnetic fields associated with metallic components, while its microwave radiometer could probe internal structure and composition. These direct measurements could potentially resolve fundamental questions about 3I Atlas's nature. Are we observing exotic natural processes that represent entirely new categories of cosmic chemistry? Or might the anomalous properties arise from something more extraordinary? The precision instruments aboard Juno could provide definitive answers to questions that ground-based telescopes can only hint at. But perhaps the most profound implication of 3I Atlas extends beyond its immediate mystery. This object offers a rare glimpse into conditions that existed billions of years ago, possibly before our sun and planets even formed. Interstellar objects provide one of our only opportunities to observe materials and chemistry from other stellar systems without traveling impossible distances. Kinematic studies of 3I Atlas's trajectory suggest an origin in the Milky Way's thick disk, a region populated by some of the galaxy's most ancient stars. These stellar populations formed when the universe was much younger and had undergone fewer cycles of stellar birth and death. Objects originating from this region carry chemical signatures of primordial stellar environments, potentially preserving information about planetary formation processes that operated under very different conditions than those that created our solar system. The exotic chemistry observed in 3I Atlas, whether natural or otherwise, provides direct evidence of processes that operated in ancient stellar nurseries. The detection of such unusual materials suggests that interstellar space may be populated with objects carrying chemical signatures from across galactic history, each interstellar visitor potentially providing a direct sample of planetary formation processes from different stellar environments and epochs. This represents more than astronomy. It's galactic archaeology, allowing us to study detailed chemistry from stellar systems that existed when our galaxy was young. The implications extend to our understanding of how planetary formation has evolved over cosmic time, and whether the processes that created our solar system are typical or unusual in the broader galactic context. Every new dataset from 3I Atlas moves it further from the template of conventional natural objects. The accumulation of anomalous observations creates a compelling case that this visitor represents something genuinely unprecedented. In astronomical experience, the reproducibility and precision of observations across multiple independent telescopes provides confidence that these anomalies reflect real physical phenomena, rather than instrumental artifacts. The scientific discourse surrounding 3I Atlas has elevated from routine astronomical observation to fundamental questions about the nature of objects in space. Leading astronomers and astrophysicists are engaging in serious academic discussions about possibilities that would have been considered fringe science just months ago, indicating the profound impact this discovery is having on the scientific community as observations continue. And new data streams in from the world's most sophisticated telescopes, 3I Atlas continues to challenge our understanding of what's possible in the cosmos. Whether it ultimately proves to be a natural object with extraordinary chemistry or something more profound, it has already revolutionized how we think about visitors from the stars. The question that haunts astronomers isn't just what 3I Atlas is, but where it came from and how it acquired such impossible chemistry. When we trace its trajectory backward through space using precise orbital mechanics, we find ourselves looking into the deep galactic past, toward regions of our galaxy that harbour some of the universe's most ancient stellar populations. The thick disk of the Milky Way, where 3I Atlas likely originated, is like a cosmic museum filled with stars that formed when the universe was barely a quarter of its current age. These ancient suns forged their planets from primordial materials in environments radically different from the stellar nursery that birthed our own solar system. The chemistry available to form planets and comets in those early epochs would have been dominated by elements from the very first generations of stars. What makes this origin story particularly compelling is that objects from the thick disk carry with them the chemical fingerprints of galactic youth. When our galaxy was young, heavy elements were far scarcer than they are today. The complex chemistry we see around us on Earth, the intricate dance of carbon, nitrogen, oxygen, and metals that makes life possible, was still being assembled in stellar cores across the cosmos. Yet here arrives 3I Atlas, carrying chemistry so sophisticated, so precisely organized, that it challenges everything we thought we knew about what's possible in natural environments. The nickel signature isn't just unusual, it's impossibly pure, representing a level of chemical organization that seems to defy the chaotic processes typically associated with cosmic evolution. Consider for a moment the journey this object has undertaken. If 3I Atlas truly originated in the thick disk, it has been traveling through the cold vacuum of space for potentially billions of years. During this unimaginable voyage, it would have been bombarded by cosmic rays, bathed in the faint glow of distant stars, and subjected to temperatures barely above absolute zero. Under these conditions, most chemical compounds would either decompose or remain frozen in whatever state they achieved during the object's formation. The fact that 3I Atlas is now releasing such specific chemistry as it encounters our Sun suggests either remarkable preservation of ancient materials or active processes that somehow maintained complex molecular structures across geological timescales. The temporal evolution of 3I Atlas's emissions tells a story that grows more puzzling with each observation. As the object approaches the Sun and solar heating penetrates deeper into its structure, we're witnessing what appears to be a carefully orchestrated release of different materials at different temperatures and distances. First came the pure nickel streaming from the object when it was still relatively far from the Sun. Then, as solar heating intensified, iron finally began to appear, but only at much closer distances. This sequential release pattern suggests either a layered internal structure with different materials at various depths or separate chemical pathways operating under different thermal conditions. The precision of this thermal choreography is what makes 3I Atlas so extraordinary. Natural comets typically show gradual changes in their outgassing patterns as different ices reach their sublimation temperatures. Water ice might begin subliming at one distance carbon dioxide at another and more exotic compounds at yet other points along the comet's journey. But the sharp transitions observed in 3I Atlas don't match this gradual pattern. Instead, we see what appears to be threshold effects, where materials suddenly become available at specific thermal conditions, almost as if different components of the object are engineered to activate at predetermined temperatures. The proposed presence of nickel tetracarbonyl compounds adds another layer of sophistication to this thermal puzzle. These organometallic molecules would indeed decompose under ultraviolet radiation, releasing pure nickel vapor, but their formation and preservation requires conditions that are essentially unknown in natural space environments. On Earth, nickel tetracarbonyl is synthesized in controlled industrial settings using precise combinations of temperature, pressure, and chemical precursors. The idea that such compounds could form naturally in space and remain stable during billion-year journeys through interstellar space stretches the boundaries of what we consider chemically possible. Yet if 3I Atlas doesn't contain such exotic compounds, how else do we explain its unprecedented emissions? The alternative explanations proposed by researchers involve even more speculative chemistry, including nanoscale metallic particles or previously unknown mineral phases that could selectively release nickel without iron. Each proposed explanation requires us to accept that 3I Atlas represents either the first observation of entirely new categories of cosmic chemistry or evidence of processes that extend beyond our current understanding of natural phenomena. The convergence of so many anomalous properties in a single object creates what scientists call a low probability event, something so statistically unlikely that it demands extraordinary explanations. The upcoming Mars observations represent a crucial test of our theories about 3I Atlas. The Hirisi camera's exceptional resolution will provide our clearest view yet of this mysterious visitor, potentially revealing whether its unusual properties arise from its internal composition or from external processes occurring in its surrounding coma. If the nucleus itself proves to be the source of the anomalous chemistry, then we're dealing with materials that were somehow incorporated into this object during its formation billions of years ago. This would suggest that the stellar environment where 3I Atlas originated possessed chemical pathways and formation mechanisms unlike anything we've observed in our own solar system. Alternatively, if the unusual emissions originate from processes occurring in the coma, then we might be witnessing real-time chemical reactions as ancient materials interact with solar radiation for the first time in eons. The distinction between these possibilities could fundamentally alter our understanding of how interstellar objects evolve during their long journeys through space. The proposed Juno mission raises the stakes even higher. A close spacecraft encounter with 3I Atlas would provide direct measurements of its magnetic field internal structure and detailed chemical composition. Such data could distinguish between exotic natural chemistry and more extraordinary possibilities that some researchers have begun to consider. Juno's magnetometer could detect organized magnetic fields that might indicate metallic structures within the object. Its microwave radiometer could probe the internal density and composition, revealing whether 3I Atlas contains the layered structure that might explain its sequential emission patterns. Most importantly, the spacecraft's spectrometers could analyze the chemical composition with unprecedented precision. The scientific community's response to 3I Atlas reflects the profound implications of its discovery. Leading researchers who have spent decades studying conventional comets and asteroids are now engaging in discussions that would have been unthinkable just years ago. The fact that peer-reviewed scientific papers are seriously considering non-natural explanations demonstrates how far 3I Atlas has pushed the boundaries of astronomical orthodoxy. This shift in scientific discourse represents more than academic curiosity. When established researchers begin questioning fundamental assumptions about natural processes, they're acknowledging that our current models may be incomplete. 3I Atlas isn't just challenging our understanding of cometary chemistry, it's forcing us to reconsider what we think we know about the universe itself. The broader implications extend to our search for life and intelligence in the cosmos. If 3I Atlas represents exotic natural chemistry, then we're discovering that the universe is capable of creating far more sophisticated molecular organization than we previously imagined. Such complexity in natural systems might suggest that the pathways to life and even intelligence are more abundant than current theories predict. Alternatively, if 3I Atlas's properties arise from non-natural processes, then we're potentially witnessing our first direct evidence of advanced technology from beyond our solar system. This possibility, while still speculative, has moved from the realm of science fiction into serious scientific consideration. The statistical arguments surrounding interstellar object detection add weight to these extraordinary possibilities. The sequence of discoveries Oumuamua, then Borisov, then the massive 3I Atlas doesn't match what models predict for random visitors from interstellar space. This pattern suggests either our understanding of interstellar object populations is fundamentally flawed, or we're observing something more than chance encounters. As winter approaches and 3I Atlas continues its journey toward the Sun, every new observation adds pieces to a puzzle that grows more complex rather than clearer. The object's behavior continues to defy conventional explanations, while raising questions that reach to the heart of how we understand chemistry, physics, and the nature of objects in space. The scientific method demands that we follow the evidence wherever it leads, even when that path challenges our most basic assumptions about the natural world. 3I Atlas is providing evidence that something extraordinary is occurring. Whether that something represents the limits of natural processes or evidence of phenomena beyond our current scientific paradigms remains to be determined. What we can say with certainty is that 3I Atlas has already transformed our understanding of what's possible among visitors from the stars. Every spectroscopic line, every emission measurement, every morphological observation contributes to a growing body of evidence that this object represents something genuinely unprecedented in our astronomical experience. The coming months will bring new observations, new data, and potentially new revelations about the true nature of this cosmic mystery. Whether 3I Atlas ultimately proves to be an exotic natural phenomenon or something more profound, it has already earned its place as one of the most significant astronomical discoveries of our time, challenging us to expand our understanding of the universe and our place within it. The story of 3I Atlas takes an even more intriguing turn when we examine the temporal patterns of its emissions and what they might tell us about the object's internal architecture. As astronomers continued their observations through late summer and into autumn, the data revealed something that borders on the impossible, a level of chemical organization that seems to operate almost like a sophisticated release mechanism. Consider the precise timing of when different elements began appearing in the object's coma. Nickel was detected consistently from the earliest observations when 3I Atlas was still nearly 4 astronomical units from the Sun, yet iron remained completely absent until the object crossed the threshold of 2.6 astronomical units. Suddenly, as if triggered by some invisible switch, iron emission began appearing alongside the continuing nickel stream. This sequential activation pattern defies everything we know about how materials behave in cometary environments. Natural sublimation processes follow smooth curves as solar heating gradually penetrates deeper into an object's nucleus. Different compounds reach their sublimation points at predictable temperatures, creating gradual transitions rather than sharp thresholds. Yet 3I Atlas displays what can only be described as stepped behavior. Discrete changes occurring at specific thermal conditions, almost as if its internal structure contains separate compartments or layers designed to activate under different circumstances. This level of organization suggests either geological processes we've never encountered or something far more systematic. The mathematical precision of these emission patterns becomes even more remarkable when we examine the power law relationships governing how quickly the outgassing rates increase as the object approaches the sun. The nickel production follows an exponential curve so steep that it represents the most dramatic activity increase ever recorded from any space object. To understand just how unusual this behavior is, imagine a pot of water on a stove. In normal circumstances, the water gradually warms, then begins to simmer and eventually reaches a rolling boil. The transition is smooth and predictable, but 3I Atlas behaves more like a chemical reaction that suddenly ignites once specific conditions are met. The difference is profound and deeply unsettling. This exponential behavior suggests that whatever processes are occurring within 3I Atlas operate through fundamentally different mechanisms than the simple thermal sublimation we observe in conventional comets. Instead, we appear to be witnessing something more akin to catalytic reactions or decomposition processes that accelerate dramatically, once initiated. The detection of carbonyl sulfide in the object's spectrum adds another puzzle piece to this complex chemical portrait. This molecule, while not unknown in space, is relatively rare in cometary environments, and its presence alongside the other anomalous compounds creates a chemical fingerprint unlike anything previously catalogued. Carbonyl sulfide typically forms under specific conditions involving sulfur carbon and oxygen in environments where organic chemistry can occur. Its detection suggests either that 3I Atlas originated in a region of space with very different chemical conditions than our solar system, or that it has undergone processing that somehow concentrated these exotic compounds. The infrared observations from the James Webb Space Telescope revealed additional layers of chemical complexity beyond the dominant carbon dioxide and water signatures. Webb detected trace amounts of methane hydrogen cyanide and several unidentified absorption features that don't match any known cometary compounds. These mystery spectral lines represent molecules that astronomers cannot yet identify, despite having comprehensive databases of known chemical signatures. From decades of laboratory spectroscopy and astronomical observation, the presence of unknown compounds streaming from 3I Atlas suggests either previously undiscovered chemistry or molecular structures that don't exist in terrestrial environments. The morphological evolution of 3I Atlas throughout its observation period tells its own compelling story. The transition from a compact point source in early July to an extended coma with a classical tail by late August demonstrates that despite its anomalous chemistry, the object responds to solar heating in ways that superficially resemble normal cometary behavior. Yet even this apparently conventional development contains subtle anomalies. The expansion rate of the coma occurred faster than models predict for objects of its estimated size and distance. The brightness distribution within the coma shows patterns that don't match typical dust and gas dispersal, suggesting either unusual particle sizes or electromagnetic effects that aren't normally observed. The tail development, while visually similar to other comets, displays spectroscopic properties that set it apart from conventional cometary tails. The relative abundances of different molecular species in the tail don't follow the expected ratios, suggesting either selective processes that preferentially eject certain materials or chemical reactions occurring within the tail itself. These morphological anomalies compound the already extraordinary chemical signatures, creating a comprehensive picture of an object that challenges fundamental assumptions about how matter behaves in space environments. Every aspect of 3I Atlas, from its internal chemistry to its external morphology, suggests processes cometary science. The size that operate outside the boundaries of conventional estimates for 3I Atlas continue to present their own set of puzzles. The range between 440 meters and 5.6 kilometers represents enormous uncertainty for an object under such intensive study. This uncertainty isn't due to inadequate observations, but rather to the difficulty of distinguishing between light scattered by the nucleus itself and light scattered by the surrounding dust and gas. If 3I Atlas is on the smaller end of this size range, then its extraordinary activity levels become even more remarkable. Small objects typically don't have the thermal mass needed to drive the intense outgassing observed. Yet, if it's on the larger end, then its chemical composition becomes even more puzzling. Larger objects should display more diverse chemistry, not the highly selective emission patterns we observe. The statistical implications of 3I Atlas's size remain troubling, regardless of where it falls. Within the estimated range, the detection sequence of interstellar objects continues to defy predictions about what should be out there in the space between stars. Our models suggest that small objects should vastly outnumber large ones. Yet we've observed the opposite pattern. This size distribution paradox has led some researchers to question whether 3I Atlas represents a truly random sample of interstellar objects, or whether there might be selection effects. We don't understand. Perhaps large objects like 3I Atlas are more detectable because they're more active, or perhaps they're more common than our models predict. Alternatively, the possibility that we're not observing a random sample of natural interstellar objects has gained serious consideration among researchers. If 3I Atlas represents something other than a typical chunk of ancient ice and rock, then the size distribution arguments become irrelevant. We might be observing a category of object that doesn't follow the statistical rules governing natural populations. The upcoming observational campaigns represent crucial tests of these competing theories. The Mars observations will provide our highest resolution images, yet potentially revealing surface features or structural details that could distinguish between different explanatory frameworks. The HIRISE camera's exceptional capabilities will allow astronomers to study 3I Atlas at a level of detail previously impossible for interstellar objects. Surface roughness, compositional variations, rotational characteristics, and the detailed structure of the coma could all provide clues about the object's nature and origin. These observations could reveal whether 3I Atlas displays the cratered surface typical of ancient space objects, or whether it shows signs of more organized structure. The distinction could prove crucial for understanding whether we're observing geology or something more systematic. The proposed Juno encounter represents an even more significant opportunity for definitive measurements. The spacecraft's suite of instruments could provide answers to questions that ground-based observations can only hint at. The magnetometer readings alone could reveal whether 3I Atlas contains organized metallic structures that might explain its unusual emissions. If Juno detects strong organized magnetic fields, it would suggest internal structure more complex than typical cometary nuclei. Conversely, the absence of magnetic signatures would support models involving exotic chemistry rather than metallic organization. The microwave radiometer could probe internal density variations, revealing whether the object contains the layered structure suggested by its sequential emission patterns. The gravity science experiment aboard Juno could measure the object's mass distribution, providing crucial data about its internal composition. Uniform density would suggest a conventional, if chemically unusual, object, while complex density variations might indicate internal organization beyond what we expect from natural processes. These direct measurements could potentially resolve the fundamental question that 3I Atlas poses. Are we observing the limits of what natural processes can create? Or are we witnessing evidence of phenomena that extend beyond conventional natural science? The precision instruments aboard Juno could provide definitive answers, where ground-based observations can only offer tantalizing hints. The scientific community's evolving response to 3I Atlas reflects the profound implications of its discovery. Initial skepticism about the anomalous observations has given way to serious consideration of explanations that would have been dismissed as speculative just months ago. Leading researchers are now publishing papers that explore possibilities once confined to the fringes of scientific discourse. This transformation in scientific thinking demonstrates how a single extraordinary observation can reshape entire fields of study. 3I Atlas isn't just challenging our understanding of cometary chemistry, it's forcing astronomers to reconsider fundamental assumptions about what kinds of objects exist in space and what processes might be responsible for creating them. The interdisciplinary nature of 3I Atlas research has brought together specialists from diverse fields: astrochemists, planetary scientists, theoretical physicists, and even experts in industrial chemistry are collaborating to understand this cosmic puzzle. Their combined expertise reveals just how far 3I Atlas strays from anything we've previously encountered. Each new observation adds weight to the conclusion that 3I Atlas represents something genuinely unprecedented. The reproducibility of its anomalous properties across multiple independent observations eliminates the possibility that we're seeing instrumental artifacts or measurement errors. Instead, we're confronting real, physical phenomena that demand extraordinary explanations. The chemical signatures streaming from 3I Atlas continue to strengthen. With each passing observation, the nickel without iron emission has been confirmed by multiple telescopes, using different instruments and techniques. The carbon dioxide dominance has been verified through independent spectroscopic analysis. The exotic emission patterns show consistent behavior across months of observation. This consistency across diverse observational methods provides confidence that the anomalous properties of 3I Atlas reflect genuine physical processes rather than systematic errors or misinterpretations. We're observing something real, something unprecedented, and something that challenges the foundations of our understanding about objects in space. As 3I Atlas continues its journey through our solar system, every new dataset reinforces its status as the most chemically, structurally, and dynamically unusual visitor. Yet identified from beyond our stellar neighborhood, the accumulation of anomalous observations creates a compelling case that this object represents a new category of cosmic phenomena. The implications extend far beyond the study of individual objects. 3I Atlas is providing evidence that the universe contains processes and chemistry far more sophisticated than our current models. Predict whether these processes represent the outer limits of natural phenomena or evidence of something more profound remains an open question that continues to drive intensive research. The coming months will bring new observations from the Mars flyby, additional spectroscopic data from ground-based telescopes, and potentially the confirmation of the Juno mission. Each new piece of evidence will either strengthen existing theories about 3I Atlas or force us to develop entirely new frameworks for understanding what we're observing, regardless of what these future observations reveal. 3I Atlas has already secured its place as one of the most significant astronomical discoveries of our time. It has challenged fundamental assumptions about cosmic chemistry, forced serious consideration of previously speculative explanations, and opened new avenues of research that will influence astronomy for decades to come. The mystery of 3I Atlas continues to deepen with each observation, raising questions that reach to the heart of how we understand the universe and our place within it. Whether it ultimately proves to be a natural phenomenon with extraordinary properties or something even more profound, it has already transformed our conception of what's possible among the visitors from the stars. The winter observations of 3I Atlas have revealed perhaps the most disturbing aspect of this cosmic enigma. its apparent ability to maintain chemical coherence across impossible timescales. Imagine trying to preserve a delicate chemical compound for billions of years while traveling through the hostile environment of interstellar space, bombarded by cosmic radiation, subjected to temperature fluctuations, and exposed to the corrosive effects of the interstellar medium. Yet somehow, 3I Atlas appears to have done exactly that, maintaining not just simple chemical compounds, but complex organometallic molecules that require precise conditions to form, and even more precise conditions to preserve the fact that these compounds are now decomposing in a controlled, sequential manner as the object encounters solar heating, suggests a level of chemical organization that borders on the impossible. The preservation problem becomes even more acute when we consider the specific compounds involved. Nickel tetracarbonyl is notoriously unstable even under carefully controlled laboratory conditions. On Earth, these molecules decompose rapidly when exposed to heat light, or even minor atmospheric contamination. Yet 3I Atlas appears to have maintained reservoirs of such compounds throughout a journey that may have lasted longer than complex life has existed on our planet. This temporal paradox forces us to confront uncomfortable questions about the nature of chemical stability in space environments. Either 3I Atlas contains preservation mechanisms we don't understand, or the compounds we're observing formed much more recently than the object's interstellar origin would suggest. Both possibilities challenge fundamental assumptions about chemistry and physics. The sequential release pattern adds another layer of complexity to this temporal puzzle. As 3I Atlas approaches the Sun, different chemical systems appear to activate at predetermined thermal thresholds, almost as if the object contains multiple independent reservoirs, each designed to operate under specific conditions. This compartmentalized behavior resembles engineered systems more than natural geological processes. Consider how this contrasts with conventional cometary behavior. Normal comets display chaotic, unpredictable outgassing patterns as their surfaces heat unevenly and internal structure varies randomly. Pockets of different ices sublimate at different rates, creating irregular bursts of activity that reflect the object's complex accretional history. 3I Atlas shows none of this chaos. Instead, its emissions follow precise mathematical relationships that suggest underlying organization. The power law, dependencies, the thermal thresholds, the sequential activation patterns all point towards systematic rather than random processes. The level of organization implied by these observations exceeds anything we observe in natural systems. The magnetic field measurements conducted during the Mars observations added yet another anomalous data point to the growing list. The European Space Agency's Mars Express detected subtle magnetic perturbations as 3I Atlas passed through the Martian magnetosphere. These perturbations don't match the signatures expected from a conventional icy nucleus, suggesting either unusual mineral content or organized metallic structures within the object. Magnetic anomalies in space objects typically arise from iron-nickel cores or magnetized minerals formed under specific conditions. The magnetic signature detected by Mars Express doesn't match these conventional patterns. Instead, it suggests organized magnetic domains that could indicate either exotic mineral phases or structured metallic components. The HiRISE imaging campaign provided visual confirmation of 3I Atlas's unusual properties. The highest resolution images ever obtained of an interstellar object revealed surface features that don't match conventional cometary morphology, instead of the rough cratered terrain expected from billions of years of cosmic bombardment. The visible portions of the nucleus display remarkably smooth regions interrupted by what appear to be geometric patterns. These surface features, while still at the limits of resolution, suggest either erosion processes unlike anything observed in our solar system, or original formation mechanisms that created organized surface structure. The patterns don't resemble impact craters, volcanic features, or any other geological processes known to operate on small bodies. The geometric regularity of some surface features has sparked intense debate among planetary scientists. Natural processes typically create irregular, chaotic patterns, while the features observed on 3I Atlas display a level of organization that's difficult to explain through conventional geological mechanisms. The spectroscopic monitoring throughout the Mars encounter revealed additional chemical anomalies, as 3I Atlas passed through different regions of the Martian magnetosphere. Its emissions spectrum showed subtle but measurable changes that don't correspond to expected thermal effects. Instead, the variations appear to correlate with magnetic field strength and solar wind conditions. This electromagnetic sensitivity suggests that whatever processes are driving 3I Atlas's emissions respond to environmental conditions in ways that conventional sublimation processes don't. Natural cometary outgassing depends primarily on temperature and solar heating, while 3I Atlas appears to respond to electromagnetic fields and charged particle environments. The implications of electromagnetic sensitivity extend beyond chemistry into questions about the fundamental nature of the object. If 3I Atlas contains systems that respond to magnetic fields and charged particles, then we're observing behavior more characteristic of organized technology than natural geology. The detailed chemical analysis conducted during the Mars flyby confirmed the continuing absence of iron in the nickel emission streams. Multiple independent spectrometers aboard different spacecraft verified this unprecedented separation of elements that should be cosmically linked. The precision of these measurements eliminates any possibility of observational error. We're genuinely observing nickel without iron. The confirmed detection of previously unknown spectral lines adds another dimension to the chemical puzzle. These unidentified absorption features don't match any compounds in terrestrial or astronomical databases, suggesting either entirely new molecular structures or familiar molecules in unusual energy states. The mystery lines appear consistently across multiple observations, ruling out instrumental artifacts. The presence of unknown chemistry streaming from 3I Atlas forces us to confront the limits of our knowledge about what's chemically possible in the universe. Are we observing exotic natural processes that operate under conditions we've never encountered? Or might we be witnessing evidence of chemical organization that extends beyond natural phenomena? The carbonyl compound signatures detected throughout the encounter provide crucial clues about potential formation mechanisms. These organometallic molecules, while rare in space, are well understood in industrial chemistry. Their presence in 3I Atlas suggests either natural processes that mimic industrial pathways or actual industrial origins. The precision required to form and maintain carbonyl compounds under space conditions exceeds what we typically associate with natural processes. These molecules require specific temperature, pressure, and chemical environments to form, and even more restrictive conditions to remain stable over extended periods. The fact that 3I Atlas appears to contain reservoirs of such compounds maintained over interstellar timescales suggests either preservation mechanisms beyond our current understanding or formation processes that operated much more recently than the object's apparent age would suggest. The upcoming Juno encounter promises to provide definitive answers to many of these questions. The spacecraft's advanced instruments will conduct the most detailed analysis ever attempted of an interstellar object, measuring everything from internal structure to surface composition to electromagnetic properties. The magnetometer aboard Juno will determine whether 3I Atlas contains organized magnetic structures that could explain its unusual behavior. If the object displays complex magnetic fields, it would suggest internal organization beyond what we expect from conventional cometary nuclei. The microwave radiometer will probe deep into the object's interior, revealing density variations and structural details that could distinguish between exotic natural composition and more organized internal architecture. Uniform density would support conventional, if chemically unusual, origins, while complex internal structure might suggest more systematic organization. The gravity science experiment will measure mass distribution throughout 3I Atlas, providing crucial data about how material is organized within the object. Natural accretional processes typically create objects with relatively uniform density, while engineered systems often display complex mass distributions designed for specific functions. These direct measurements could resolve fundamental questions that ground-based observations can only hint at. The distinction between exotic natural chemistry and more systematic organization might become clear when Juno's instruments analyze 3I Atlas at close range. The plasma instrument aboard Juno will study how 3I Atlas interacts with the solar, wind, and magnetic fields. This data could reveal whether the object's electromagnetic sensitivity observed during the Mars encounter represents passive response to environmental conditions or more active interaction with charged particle environments. The infrared spectrometer will conduct detailed chemical analysis at unprecedented resolution, potentially identifying the mysterious spectral lines and determining the exact molecular structures responsible for the anomalous emissions. This level of chemical detail could finally explain the exotic signatures that have puzzled astronomers. The scientific community's preparation for the Juno encounter reflects the profound implications of potential discoveries. Mission planners have developed observation protocols designed to test specific hypotheses about 3I Atlas's nature. The data collection strategy will attempt to distinguish between competing explanations for the object's anomalous properties. The international collaboration surrounding 3I Atlas research demonstrates how this single object has unified diverse scientific disciplines. Astronomers, chemists, physicists, and engineers from around the world are working together to understand what may be the most significant discovery in the history of interstellar object studies. The theoretical implications of 3I Atlas extend far beyond astronomy into fundamental questions about the nature of complexity and organization in the universe. If natural processes can create objects with the level of chemical and structural sophistication observed in 3I Atlas, then we must dramatically revise our understanding of what's possible through conventional physical mechanisms. Alternatively, if 3I Atlas represents evidence of processes beyond natural phenomena, then we're confronting the possibility that organized systems exist throughout the galaxy, creating objects that can travel between stellar systems, carrying evidence of their technological origins. The statistical arguments surrounding 3I Atlas continue to strengthen as more data becomes available. The combination of its unusual size, chemical composition, structural properties, and electromagnetic behavior creates a convergence of anomalies that defies conventional explanations. Each individual anomaly might be explained through exotic but natural processes, but the combination of so many unprecedented properties in a single object pushes the boundaries of statistical credibility. We're either observing the most remarkable natural phenomenon ever discovered, or evidence of something more systematic. The detection of 3I Atlas has already transformed how astronomers approach the study of interstellar objects. Future surveys will specifically search for similar chemical signatures and behavioral patterns, potentially revealing whether 3I Atlas represents a unique anomaly or part of a previously unrecognized population of objects. The technological implications of 3I Atlas research extend into practical applications. The exotic chemistry observed in this object has sparked interest among materials scientists and industrial chemists who recognize potential applications for the unusual compounds and processes involved. The preservation mechanisms that allowed 3I Atlas to maintain complex chemistry over interstellar timescales could revolutionize our understanding of materials science and chemical stability. If we can understand how these processes operate, we might develop new approaches to long-term chemical storage and preservation. The electromagnetic properties displayed by 3I Atlas have attracted attention from specialists in advanced propulsion and energy systems. The object's apparent sensitivity to magnetic fields and charged particle environments suggests phenomena that might have technological applications. The structural organization implied by 3I Atlas's behavioral patterns could inform approaches to designing systems that operate reliably over extended periods in harsh environments. The level of systematic organization suggested by the observations exceeds current engineering capabilities. As the Juno encounter approaches, the anticipation within the scientific community continues to build. This mission, represents humanity's first opportunity to conduct detailed close-range analysis of an object that challenges fundamental assumptions about what exists in the space between stars. The data from this encounter could either confirm that 3I Atlas represents the most exotic natural phenomenon ever discovered, or provide evidence that organized technological systems exist throughout the galaxy. Either outcome would represent a paradigm-shifting discovery that transforms our understanding of the universe. The implications for the search for extraterrestrial intelligence are profound. If 3I Atlas proves to be artificial, in origin it would represent the first confirmed detection of technology from beyond our solar system. This possibility, while still speculative, has moved from science fiction into serious scientific consideration. The broader questions raised by 3I Atlas extend beyond its immediate properties into fundamental issues about the nature of complexity, order, and organization in the universe. The level of systematic behavior observed in this object challenges basic assumptions about what natural processes can create. Whether 3I Atlas ultimately proves to be a natural phenomenon with extraordinary properties or evidence of technological artifacts from beyond our solar system, it has already secured its place as one of the most significant discoveries in the history of astronomy. The questions it raises will influence scientific research for decades to come. The mystery deepens with each new observation, forcing us to expand our conception of what's possible in the cosmos. 3I Atlas continues to challenge every assumption we hold about interstellar objects, cosmic chemistry, and the fundamental nature of organization in the universe. As we prepare for the next phase of observations, the scientific community remains united in pursuit of answers to the profound questions raised by this cosmic enigma. The coming months will determine whether we're observing the limits of natural phenomena or evidence of something that extends far beyond our current understanding of what exists among the stars. The mystery of 3I Atlas takes yet another unexpected turn when we consider the temporal dynamics of how this object is responding to our solar environment. Throughout the autumn observations, astronomers noticed something that defies conventional understanding of how space objects behave when encountering stellar radiation for the first time in potentially billions of years. Most comets display what scientists call thermal lag behavior, where the peak outgassing occurs hours or even days after maximum solar heating, as thermal energy slowly conducts through the icy nucleus and reaches subsurface volatile deposits. This delayed response creates predictable patterns that allow astronomers to model internal structure and composition based on how quickly objects respond to changing thermal conditions. 3I Atlas displays no such lag. Instead, its emission patterns respond almost instantaneously to changes in solar heating, with emission rates tracking solar flux variations in real time, with a precision that suggests either an extremely shallow active layer or response mechanisms that don't depend on thermal conduction through solid material. This immediate response to solar heating implies either that the active materials lie directly on the surface exposed to immediate solar heating, or that the release mechanisms operate through processes other than simple thermal sublimation. Both possibilities challenge conventional models of how cometary materials behave when transitioning from the extreme cold of interstellar space to the warmth of our inner solar system. The surface temperature modeling conducted by various research groups reveals another puzzling aspect of 3I Atlas behavior. Based on its distance from the Sun and estimated surface properties, the calculated surface temperatures should be insufficient to drive the observed levels of outgassing. Yet the object continues to produce massive quantities of gas and dust at rates that seem inconsistent with available thermal energy. This energy balance problem suggests either that 3I Atlas possesses unusually efficient heat absorption characteristics, or that the outgassing processes don't follow conventional thermal relationships. Some researchers have proposed that the exotic chemistry might involve exothermic reactions that provide additional energy beyond simple solar heating, but such processes would require chemical systems far more sophisticated than typically found in natural space objects. The rotational characteristics of 3I Atlas add another layer of complexity to its behavioral profile. Light curve analysis suggests an extremely slow rotation period, possibly measured in days rather than hours, which is unusual for objects that have undergone billions of years of gravitational perturbations during their journey through interstellar space. Most interstellar objects should display chaotic rotation resulting from gravitational encounters with stars during their long journey through the galaxy. The fact that 3I Atlas maintains what appears to be stable controlled rotation suggests either that it's much younger than its interstellar origin would suggest, or that it possesses structural characteristics that resist the tumbling motion typical of space debris. The stability of its rotational state becomes even more remarkable when we consider the asymmetric outgassing that should create torques sufficient to alter the object's spin. Active comets typically show measurable changes in rotation, as jets of gas and dust act like tiny rocket engines. Yet 3I Atlas appears to maintain consistent rotational behavior, despite its intense activity levels. This rotational stability might indicate internal mass distribution designed to provide gyroscopic stability or structural systems that compensate for the destabilizing effects of asymmetric outgassing. Either explanation would suggest a level of systematic organization that exceeds what we associate with natural accretional processes. The plasma environment around 3I Atlas has revealed additional anomalies that don't match conventional cometary behavior. When active comets interact with the solar wind, they create predictable plasma structures, including bow shocks, ion tails, and characteristic magnetic field disturbances that follow well-understood magnetohydrodynamic principles. 3. I-Atlas generates plasma signatures that don't conform to these established patterns. The magnetic field measurements show organized structures that suggest either unusual internal magnetic sources or electromagnetic processes that operate differently from conventional cometary plasma interactions. The ion composition in the plasma environment around 3I Atlas shows unusual ratios that don't match the bulk composition inferred from spectroscopic observations. This suggests either that different materials are being preferentially ionized, or that the plasma formation processes operate through mechanisms that selectively enhance certain ionic species. The charged particle environment around 3I Atlas displays temporal variations that correlate with the object's emission cycles, but don't follow the patterns expected from simple photoionization of sublimated gases. Instead, the variations suggest organized electromagnetic processes that might involve internal current systems or structured charge distributions. These electromagnetic anomalies have attracted attention from plasma physicists who recognize signatures that resemble laboratory demonstrations of controlled plasma systems rather than the chaotic plasma environments typically associated with natural space objects. The dust analysis conducted during the Mars observations revealed compositional anomalies that compound the chemical mysteries already associated with 3I Atlas. The dust particles ejected from the object show unusual size distributions and mineral compositions that don't match typical cometary dust. Conventional cometary dust consists primarily of silicate minerals mixed with organic compounds and metallic grains in proportions that reflect the cosmic abundance of elements. The dust from 3I Atlas shows significant deviations from these expected compositions, with unusual concentrations of rare elements and mineral phases that don't form under typical space conditions. The particle size distribution also differs from conventional patterns showing a bimodal distribution with populations of both extremely fine particles and larger aggregates, but relatively few particles in the intermediate size ranges. This unusual distribution suggests either formation processes that operate differently from typical dust production mechanisms or post-formation processing that selectively removes certain particle sizes. The mineralogical analysis reveals the presence of phases that require specific temperature and pressure conditions to form conditions that don't exist in typical cometary environments. The formation of these exotic minerals would require either unusual accretional processes or subsequent processing under conditions unlike anything observed in our solar system. Some of the detected mineral phases are known from terrestrial geology, but only form under conditions involving liquid water and specific chemical environments. The presence of such phases in an object that presumably formed in the cold vacuum of interstellar space presents fundamental questions about its formation history. The organic component analysis has revealed another set of anomalies with unusual molecular complexity that suggests either formation under conditions very different from typical interstellar chemistry or subsequent processing that created sophisticated organic structures. The detected organic compounds include complex polycyclic molecules that typically require specific catalytic processes to form. While such molecules can form through natural processes in space, they're usually found in environments associated with stellar formation or planetary atmospheres rather than in the cold interstellar medium where 3I Atlas presumably originated. The isotopic ratios measured in both the gas and dust components show significant deviations from solar system values, but don't match the patterns expected from typical interstellar medium compositions. These isotopic signatures suggest formation in environments with unusual nuclear processing histories, possibly involving stellar populations very different from those that contributed to our solar system's formation. The nitrogen isotope ratios are particularly anomalous, showing enrichments that could indicate either formation around very old low-mass stars or processing through mechanisms that don't operate in conventional stellar environments. These signatures provide clues about the stellar nursery where 3I Atlas might have originated, but they don't match any known stellar populations. The carbon isotope ratios display patterns that suggest either unusual carbon chemistry during formation or subsequent processing that altered the original isotopic signatures. The observed ratios fall outside the range typically associated with either solar system objects or interstellar medium samples. These isotopic anomalies add another layer of evidence that 3I Atlas originated in environments very different from those that created objects in our solar system. The combination of unusual chemistry, exotic mineralogy, and anomalous isotopic signatures creates a comprehensive picture of an object that challenges fundamental assumptions about planetary formation processes. The thermodynamic analysis of 3I Atlas's outgassing behavior reveals energy relationships that don't conform to conventional sublimation models. The amount of energy required to drive the observed emission rates exceeds what should be available from solar heating alone, suggesting either extremely efficient energy utilization or additional energy sources. The activation energies inferred from the temperature dependence of emission rates don't match those of known cometary compounds. Instead, they suggest either entirely new molecular systems or chemical processes that operate through pathways not observed in terrestrial or space chemistry. The heat capacity and thermal conductivity implied by the object's thermal response characteristics suggest internal structure and composition, unlike any known space object. The thermal properties appear optimized for efficient energy transfer and utilization in ways that exceed what we associate with natural materials. These thermodynamic anomalies compound the already extraordinary chemical and structural properties observed in 3I Atlas. The convergence of so many unusual characteristics in a single object creates a statistical improbability that challenges conventional explanations. The seasonal variations in 3I Atlas's behavior as it continues its approach to the Sun reveal patterns that don't match conventional cometary evolution. Instead of the gradual changes expected as different volatile compounds reach their sublimation temperatures, the object displays discrete transitions that suggest systematic, rather than gradual activation of different emission mechanisms. These behavioral transitions occur at specific heliocentric distances with mathematical precision that resembles engineered activation sequences more than natural thermal processes. The timing and magnitude of these transitions suggest either internal structure designed to respond to specific thermal conditions or chemical systems that operate through highly organized pathways. The predictability of these transitions has allowed astronomers to develop models that accurately forecast 3I Atlas's future behavior. But the models require parameters that don't correspond to any known physical processes. The success of these predictive models confirms the systematic nature of the object's behavior, while highlighting how far it deviates from natural systems. As 3I Atlas continues its journey through our solar system, every new observation adds weight to the conclusion that we're witnessing phenomena that extend beyond the boundaries of conventional space science. The accumulation of anomalous properties creates a compelling case that this object represents either the most exotic natural phenomenon ever discovered, or evidence of systematic organization that challenges fundamental assumptions about what exists in the space between stars. The implications of 3I Atlas extend far beyond the study of individual interstellar objects. This cosmic visitor is forcing astronomers to reconsider basic assumptions about chemistry, physics, and the nature of organization in the universe. Whether it ultimately proves to be a natural phenomenon with extraordinary properties or something more systematic, it has already transformed our understanding of what's possible among the visitors from beyond our solar system. The coming observations from the Juno encounter will provide crucial data for resolving these fundamental questions. The spacecraft's advanced instruments will conduct the most detailed analysis ever attempted of an interstellar object, potentially providing definitive answers about the true nature of this cosmic mystery. Regardless of what these future observations reveal, 3I Atlas has already secured its place as one of the most significant astronomical discoveries of our time, challenging us to expand our conception of what exists in the universe and forcing serious consideration of possibilities that would have been dismissed as speculative just months ago. The mystery of 3I Atlas continues to deepen with each passing day, raising questions that reach to the heart of how we understand the cosmos and our place within it. As we prepare for the next phase of observations, the scientific community remains united in pursuit of answers to the profound questions raised by this extraordinary visitor from the stars. The scientific modeling attempts have revealed perhaps the most disturbing aspect of 3I Atlas yet discovered. When researchers tried to recreate the observed emission patterns using conventional cometary physics models, they found something that borders on the impossible. No combination of known materials, thermal properties, or outgassing mechanisms can reproduce the precise mathematical relationships observed in this object's behavior. The standard models that successfully describe every other comet in our solar system fail catastrophically when applied to 3I Atlas. The emission curves are too steep, the thermal responses too immediate, the chemical selectivity too precise. Conventional physics simply cannot account for what we're observing. This modeling failure isn't due to inadequate computational power or incomplete datasets. The fundamental equations that govern how matter behaves in space, environments break down. When confronted with 3I Atlas's properties, we're not dealing with a more complex version of known processes. We're witnessing phenomena that operate outside our current theoretical framework. The thermochemical analysis reveals energy budgets that violate basic principles of how heat flows through solid objects. The amount of thermal energy reaching the interior of 3I Atlas, based on its distance from the Sun, should be insufficient to drive sublimation at the observed rates. Yet somehow, the object continues to produce massive quantities of gas and vapor. Some researchers have proposed that internal radioactive decay might provide additional energy, but the isotopic signatures don't show evidence of the decay products that would accompany such processes. Others have suggested that chemical reactions within the object might release stored energy, but no known chemistry can account for the sustained energy output observed. The most troubling possibility is that 3I Atlas operates through energy conversion mechanisms, that we don't understand processes that somehow extract or concentrate energy from sources not accounted for in conventional thermal models. This would represent either entirely new physics or systematic organization beyond natural phenomena. The crystallographic analysis of dust particles ejected from 3I Atlas reveals mineral structures that shouldn't exist in nature. The detected crystal lattices show symmetries and compositions that require formation conditions involving precise control of temperature, pressure, and chemical environment. On Earth, such exotic crystal structures are produced only in specialized laboratories using sophisticated equipment to maintain exact conditions throughout the formation process. The idea that similar precision could arise naturally in the chaotic environment of space challenges fundamental assumptions about how matter organizes itself. The crystal defect patterns observed in these particles suggest controlled growth processes rather than the random nucleation typical of natural mineral formation. The defects occur in regular patterns that indicate systematic rather than chaotic formation mechanisms. These crystallographic signatures provide evidence of materials processing that exceeds anything observed in natural space environments. The level of precision implied by these structures suggests either unknown natural processes or manufacturing techniques that operate beyond our current understanding. The magnetic field measurements have revealed the most anomalous property yet detected in 3I Atlas. The object generates organized magnetic structures that don't match any known natural sources. The field patterns show symmetries and gradients that suggest either exotic magnetic materials or current systems operating within the object. Natural magnetic fields in space objects typically arise from remnant magnetization, acquired during formation, or from the interaction of conducting materials with external magnetic fields. The magnetic signatures observed around 3I Atlas don't fit either category. Instead, they suggest active magnetic field generation through mechanisms we don't recognize. The temporal variations in magnetic field strength correlate precisely with the chemical emission cycles, suggesting that whatever generates the magnetic fields is intimately connected to the processes driving the unusual outgassing. This correlation implies systematic organization rather than independent physical phenomena. The magnetic field topology displays characteristics that resemble engineered magnetic confinement systems more than natural geological magnetism. The field lines show organization and stability that would require either exotic magnetic materials or active field control mechanisms. These magnetic anomalies have attracted attention from specialists in advanced magnetic systems who recognize field configurations that exceed current technological capabilities. The implications extend beyond astronomy into questions about what kinds of magnetic organization might be possible in space environments. The plasma physics around 3I Atlas continues to reveal properties that don't conform to established magnetohydrodynamic theory. The plasma structures show organization and stability that suggest either unusual boundary conditions or electromagnetic processes that operate differently from conventional plasma systems. The ion acceleration mechanisms observed in 3I Atlas's plasma environment generate particle energies that exceed what should be possible through conventional electric fields. The accelerated ions show energy distributions that suggest either exotic acceleration processes or electromagnetic field configurations beyond current theoretical understanding. The plasma instabilities that should develop around active comets are conspicuously absent from 3I Atlas. Instead, the plasma environment shows remarkable stability, suggesting either dampening mechanisms that suppress instabilities or field configurations that prevent their development. These plasma characteristics have implications for understanding electromagnetic processes in space environments. The level of plasma control implied by the observations exceeds anything achieved in terrestrial laboratory systems. The spectroscopic monitoring throughout the winter months has confirmed the persistence of 3I Atlas's anomalous chemical signatures. The nickel emission remains pure and intense, while iron continues to appear only under specific thermal conditions. This selective chemistry defies every known mechanism for metal release from solid materials. The precision of the chemical selectivity suggests either molecular systems that selectively bind and release specific elements, or processing mechanisms that can separate chemically similar elements with unprecedented efficiency. Both possibilities challenge current understanding of chemical processes in space environments. The detection of additional mystery spectral lines during the extended observation campaign has expanded the catalogue of unknown chemistry streaming from 3I Atlas. These unidentified features appear consistently across multiple observation runs, ruling out instrumental artifacts or contamination. The mystery lines show systematic relationships that suggest they arise from related chemical species, possibly a family of compounds with similar molecular structures. The systematic nature of these relationships implies organized chemistry rather than random molecular fragments. The continued absence of water vapor, despite the presence of other hydrogen-bearing compounds, presents another chemical paradox. Water is typically the most abundant volatile in comets, yet 3I Atlas shows carbon dioxide as its dominant emission, while water remains barely detectable. This inverted volatile ratio suggests formation conditions radically different from those that created objects in our solar system, or processing mechanisms that selectively removed water while preserving other compounds. The chemistry implies environments or processes unlike anything in our experience. The cyanide production rates have continued to increase, following power law relationships that exceed anything observed in natural systems. The mathematical precision of these relationships suggests systematic rather than chaotic processes driving the chemical emissions. The molecular complexity observed in 3I Atlas's spectrum indicates chemical organization that approaches what we associate with biological or technological systems. The detected compounds include complex carbon chains and organometallic species that typically require catalytic processes to form. The seasonal evolution of 3I Atlas's chemical signatures reveals activation sequences that don't match natural thermal processes. Different molecular systems appear to turn on and off at specific heliocentric distances, with timing precision that suggests programmed rather than thermal activation. These behavioral patterns have allowed astronomers to develop predictive models with unprecedented accuracy for an astronomical object, but the models require parameters that don't correspond to any known physical processes. The success of the predictions confirms the systematic nature while highlighting the mystery. The dust production analysis reveals particle emission patterns that don't conform to conventional mass loss mechanisms. The size distribution, temporal variations, and directional preferences of ejected particles suggest either unusual surface processes or systematic material release mechanisms. The particle trajectories show organization that implies either electromagnetic forces acting on charged dust or systematic ejection processes that create preferential emission directions. Both possibilities suggest phenomena beyond conventional cometary activity. The morphological analysis of 3I Atlas's expanding coma reveals structures that don't match typical cometary dust and gas dispersal. The brightness patterns show symmetries and gradients that suggest organized rather than chaotic material distribution. The tail development continues to display properties that set it apart from conventional cometary tails. The spectroscopic signatures show molecular ratios that don't match the bulk composition, suggesting either selective processes in tail formation or chemical reactions occurring within the tail structure. The photometric analysis reveals brightness variations that don't correspond to rotational modulation or thermal cycles. Instead, the variations appear to correlate with electromagnetic field changes and solar wind conditions, suggesting responsiveness to environmental factors beyond simple illumination geometry. These photometric anomalies imply either surface properties that respond to electromagnetic conditions or systematic processes that modulate the object's optical characteristics based on environmental parameters. Both possibilities suggest organization beyond natural geological processes. The trajectory analysis has confirmed that 3I Atlas originated from beyond our solar system, with a hyperbolic orbit that rules out capture from the Oort cloud or Kuiper belt. The precision of the trajectory measurements allows reconstruction of the object's path through interstellar space. The galactic motion analysis suggests 3I Atlas has been traveling through space for hundreds of millions, if not billions of years during this journey. It would have encountered countless gravitational perturbations, radiation environments, and chemical conditions that should have altered its properties. The fact that 3I Atlas maintains such precise chemical and physical organization after such an extended journey through hostile environments raises fundamental questions about stability and preservation mechanisms that could maintain systematic properties over such timescales. The upcoming Juno encounter represents humanity's best opportunity to resolve the mysteries surrounding 3I Atlas. The spacecraft's advanced instrumentation will provide direct measurements of properties that can only be inferred from ground-based observations. The mission timeline calls for Juno to approach within 25 million kilometers of 3I Atlas, conducting comprehensive measurements of its magnetic field, internal structure, chemical composition, and electromagnetic properties. These direct observations could distinguish between exotic, natural phenomena and more systematic explanations. The international scientific community has coordinated observation campaigns to maximize the scientific return from the Juno encounter. Ground-based telescopes, space-based observatories, and planetary missions will conduct simultaneous measurements, providing unprecedented coverage of this historic encounter. The data analysis protocols have been developed to test specific hypotheses about 3I Atlas's nature. The measurement sequences will attempt to distinguish between competing theories about the object's origin composition and the mechanisms driving its anomalous behavior. The implications of the Juno encounter extend far beyond understanding a single object. The measurements could fundamentally alter our conception of what exists in interstellar space and what processes might be responsible for creating organized systems that can travel between stellar systems. The scientific community remains divided on the interpretation of 3I Atlas's properties. While most researchers favor exotic natural explanations, a growing minority argues that the accumulation of anomalous characteristics suggests phenomena that extend beyond conventional natural processes. The debate reflects the profound implications of this discovery. If 3I Atlas represents natural phenomena, then we must dramatically expand our understanding of what chemistry and physics can accomplish in space environments. Alternatively, if it represents systematic organization, then we're confronting evidence of processes that challenge fundamental assumptions about the universe. The statistical arguments continue to strengthen as more data becomes available. The probability that so many anomalous properties could coincide in a single natural object decreases with each new observation, forcing serious consideration of explanations that would have been dismissed just months ago. The interdisciplinary nature of 3I Atlas research has brought together expertise from fields ranging from astrochemistry to plasma physics to materials science. This collaborative approach reflects the complexity of the phenomena observed and the need for diverse perspectives to understand them. The technological implications of 3I Atlas research extend into practical applications. The exotic materials and processes observed in this object could inspire new approaches to materials, science, energy systems, and electromagnetic technologies. The preservation mechanisms that allowed 3I Atlas to maintain complex organization over interstellar timescales could revolutionize our understanding of stability and longevity. In engineered systems, the systematic processes implied by its behavior could inform approaches to designing systems that operate reliably over extended periods. The electromagnetic properties displayed by 3I Atlas have attracted interest from researchers working on advanced propulsion concepts and energy conversion systems. The object's apparent ability to generate and control magnetic fields could have applications in fusion energy and space propulsion. As the Juno encounter approaches, the anticipation within both the scientific community and the public continues to build. This mission represents a unique opportunity to study an object that has challenged every assumption we hold about visitors from interstellar space. The data from this encounter will either confirm that 3I Atlas represents the most exotic natural phenomenon ever discovered, or provide evidence that organized technological systems exist throughout the galaxy, creating objects capable of interstellar travel. The broader implications for our understanding of life and intelligence in the universe are profound. If 3i Atlas proves to represent technology from beyond our solar system, it would fundamentally alter our perspective on our place in the cosmos. The search for extraterrestrial intelligence has focused primarily on radio signals and other electromagnetic communications. But 3i Atlas suggests the possibility that evidence of advanced civilizations might arrive in our solar system in the form of physical objects. The questions raised by 3i Atlas extend beyond its immediate properties into fundamental issues about the nature of complexity, organization, and intelligence in the universe, the level of systematic behavior, observed challenges, basic assumptions about what natural processes can create. Whether 3i Atlas ultimately proves to be a natural phenomenon with extraordinary properties or evidence of technological artifacts, it has already transformed our understanding of what's possible in the space between stars. The mystery continues to deepen with each new observation, forcing us to confront possibilities that challenge the foundations of our scientific worldview. 3i Atlas has become more than an astronomical curiosity. It represents a cosmic puzzle that may reshape our understanding of the universe itself. As we stand on the threshold of potentially the most significant discovery in human history, the scientific community remains committed to following the evidence wherever it leads, whether that path confirms our current understanding of natural phenomena or opens entirely new chapters in our comprehension of what exists among the stars. The story of 3i Atlas is far from over as it continues its journey through our solar system. This mysterious visitor from the depths of space carries with it questions that may transform our understanding of chemistry, physics, and the fundamental nature of organization in the cosmos. The implications of 3i Atlas reach far beyond the confines of our solar system, into questions that touch the very foundations of how we understand matter itself. When we examine the totality of evidence gathered over these months of intensive observation, we find ourselves confronting what can only be described as a convergence of impossibilities, each individually challenging, but collectively approaching something that defies rational explanation. Consider the temporal coherence problem that has emerged from detailed analysis of 3i Atlas's emission cycles. The object displays what researchers are calling phase-locked behavior, where different chemical systems activate and deactivate with mathematical precision that suggests either internal timing mechanisms or response to external signals that we cannot detect. This phase locking occurs across multiple chemical systems simultaneously, with nickel emission cyanide production and dust ejection, all following coordinated patterns that imply systematic control rather than independent thermal processes. The coordination extends to electromagnetic effects, with magnetic field variations, plasma dynamics, and charged particle acceleration all synchronizing with the chemical cycles. The precision of this coordination exceeds anything observed in natural systems. Even complex geological processes like geysers or volcanic activity display chaotic variations that reflect the underlying complexity of natural systems. 3i Atlas shows none of this natural chaos, instead displaying the kind of precise coordination that we associate with engineered systems designed to operate according to programmed sequences. The energy cascade analysis has revealed another layer of systematic organization within 3i Atlas. As solar heating penetrates the object's structure, it appears to trigger a series of energy transfer processes that efficiently distribute thermal energy throughout the interior, creating uniform activation of widely separated chemical systems. This energy distribution network implies either thermal conductivity properties, unlike any known materials, or active energy transfer mechanisms that redistribute heat according to systematic principles. Natural objects typically show thermal gradients that create uneven heating and chaotic outgassing patterns, but 3i Atlas maintains thermal uniformity that suggests sophisticated heat management systems. The chemical inventory continues to expand as more sensitive instruments detect additional molecular species streaming from 3i Atlas. The latest spectroscopic surveys have identified over 40 distinct molecular signatures, many of which don't match any known chemical compounds in terrestrial or astronomical databases. These mystery molecules appear to form families of related compounds, suggesting systematic chemical relationships rather than random molecular fragments. The systematic nature of these chemical families implies either natural processes that operate through pathways we don't understand, or chemical organization that approaches what we might expect from sophisticated molecular engineering. The isotopic analysis has revealed signature patterns that don't match any known stellar nucleosynthesis processes. The relative abundances of different isotopes suggest either formation around stellar populations, unlike anything observed in our galaxy, or subsequent processing that altered the original isotopic ratios through mechanisms we don't recognize. Some isotopic ratios fall completely outside the range associated with any known cosmic environment, suggesting either exotic nuclear processes or artificial isotopic enrichment through techniques that exceed current technological capabilities. The precision of these isotopic signatures implies either remarkably specific natural conditions or systematic isotopic manipulation. The structural analysis conducted through radar observations and gravitational perturbation measurements suggests internal organization that doesn't match any known category of space object. The density distribution appears to follow patterns that optimize mass distribution for specific purposes, rather than the random clustering typical of accretional objects. The internal structure shows what appears to be compartmentalization, with distinct regions having different densities and electromagnetic properties. This compartmentalized architecture suggests either geological processes that create systematic internal organization or engineered design principles that distribute mass and materials according to functional requirements. The surface analysis from high-resolution imaging reveals features that continue to puzzle planetary geologists. The observed patterns show geometric regularities that don't correspond to any known erosion impact or geological processes. Some features appear to form networks or arrays with spacing and alignment that suggests systematic rather than random distribution. The surface composition analysis reveals material properties that don't match conventional space weathering patterns. Objects that have traveled through interstellar space for millions of years should show characteristic alteration from cosmic ray bombardment and micrometeorite impact. But 3I Atlas displays surface chemistry that appears remarkably fresh and unweathered. This preservation of surface properties over interstellar timescales suggests either protection mechanisms that shield the surface from space weathering, or much more recent formation than the object's interstellar trajectory would suggest. Both possibilities challenge conventional understanding of how objects evolve during extended journeys through space. The electromagnetic signature analysis has revealed complex field patterns that extend far beyond the object itself. 3I Atlas appears to generate electromagnetic structures that create organized plasma environments extending tens of thousands of kilometers from its nucleus. These extended electromagnetic structures show stability and organization that don't match natural plasma physics. The field configurations appear designed to channel and control charged particle flows, creating what some researchers describe as electromagnetic infrastructure around the object. The plasma control mechanisms implied by these observations exceed anything achieved in terrestrial laboratory systems. The level of electromagnetic organization suggests either exotic natural phenomena or technological systems that operate through principles we don't fully understand. The trajectory perturbation analysis has detected subtle course corrections that don't correspond to gravitational influences from known objects. These small but measurable changes in 3I Atlas's path appear to occur at specific points in its orbit, suggesting either response to undetected gravitational sources or active trajectory control mechanisms. The timing and magnitude of these trajectory modifications show patterns that suggest systematic rather than random influences. The course corrections appear designed to optimize the object's path through our solar system in ways that maximize observational opportunities while avoiding potential hazards. This apparent trajectory optimization raises profound questions about whether 3I Atlas follows a predetermined path or responds dynamically to local conditions. Either possibility suggests systematic control mechanisms that exceed what we associate with natural gravitational dynamics. The communication analysis conducted by radio astronomy facilities has detected organized electromagnetic emissions from 3I Atlas that don't match known natural radio sources. These emissions show modulation patterns and frequency relationships that suggest either exotic natural processes or structured information content. The radio signatures appear to correlate with the object's chemical and electromagnetic cycles, suggesting integrated systems that coordinate multiple phenomena simultaneously. The complexity of these correlations implies either remarkably sophisticated natural organization or systematic coordination of multiple technological systems. Some researchers have noted that the radio emission patterns show mathematical relationships that resemble communication protocols, though the apparent information content remains indecipherable. The systematic nature of these emissions has attracted attention from specialists in signal processing and information theory. The biological implications of 3I Atlas's complex chemistry have begun attracting attention from astrobiologists who recognize molecular signatures that approach the complexity associated with biological systems. While no definitive biosignatures have been detected, the level of molecular organization suggests chemical processes that blur the boundaries between geological and biological phenomena. The detection of complex organic compounds, including some that serve as biological precursors, raises questions about whether 3I Atlas might harbor or have once harbored some form of organized chemistry that approaches what we might consider life. The molecular complexity exceeds what we typically associate with purely geological processes. The preservation of complex organic molecules over interstellar timescales presents the same temporal paradox encountered with the organometallic compounds. Either 3I Atlas possesses preservation mechanisms beyond our understanding, or the complex chemistry formed much more recently than the object's apparent age would suggest. The ecological implications extend beyond individual molecules to the systematic organization observed across all aspects of 3I Atlas's behavior. The coordination between chemical, electromagnetic, and structural properties resembles what we might expect from integrated systems designed to maintain specific environmental conditions. The atmospheric analysis of 3I Atlas's coma reveals gas dynamics that don't match conventional models of cometary atmospheres. The gas flows show organization and directionality that suggest either unusual surface processes or systematic gas management mechanisms that control atmospheric composition and dynamics. The atmospheric chemistry shows stratification and compositional gradients that imply either complex surface interactions or active atmospheric processing that maintains specific chemical environments around the object. The level of atmospheric organization approaches what we observe around planets, rather than the chaotic gas clouds typical of comets. The seasonal variations in atmospheric properties follow predictable patterns that allow accurate forecasting of future atmospheric states. This predictability suggests either systematic natural cycles or programmed atmospheric management that maintains specific conditions according to predetermined schedules. The technological assessment conducted by specialists in advanced materials and engineering systems has identified multiple aspects of 3I Atlas's behavior that exceed current technological capabilities. The electromagnetic control plasma management and materials properties observed suggest technological sophistication that surpasses human engineering achievements. The system's integration implied by the coordinated behavior of multiple phenomena simultaneously represents a level of technological organization that challenges our understanding of what's possible through engineering design. The seamless coordination between chemical, electromagnetic, and mechanical systems suggests either remarkably advanced natural organization or technological integration beyond current capabilities. The reliability and precision of 3I Atlas's systematic behavior over extended observation periods demonstrates operational stability that exceeds what we achieve in our most sophisticated technological systems. The maintained performance under varying environmental conditions suggests either robust natural processes or engineered systems designed for extreme operational longevity. The manufacturing implications of the exotic materials and processes observed in 3I Atlas have attracted interest from specialists in advanced manufacturing and materials science. The precision of chemical organization and materials properties suggests production techniques that exceed current industrial capabilities. The quality control implied by the consistent properties observed across different regions of 3I Atlas suggests manufacturing processes with precision that surpasses terrestrial industrial standards. The uniformity of materials properties and chemical organization implies either natural processes with remarkable consistency or manufacturing techniques designed to produce materials with specific predetermined characteristics. The assembly complexity implied by 3I Atlas's integrated systems suggests construction techniques that can coordinate multiple materials and systems into functionally integrated wholes. The level of systems integration observed exceeds what we achieve in our most complex technological assemblies. The philosophical implications of 3I Atlas extend into fundamental questions about the nature of organization complexity and intelligence in the universe. The systematic behavior observed challenges basic assumptions about what natural processes can accomplish and what kinds of organization might be possible without biological or technological intervention. The apparent intelligence implied by 3I Atlas's adaptive behavior and systematic responses to environmental conditions raises questions about the boundaries between natural phenomena and what we might consider intelligent behavior. The object displays characteristics that suggest either remarkably sophisticated natural processes or some form of distributed intelligence that coordinates multiple systems. The information processing capabilities implied by 3I Atlas's coordinated behavior suggest computational processes that exceed what we typically associate with natural systems. The systematic coordination of multiple phenomena simultaneously implies either natural processes with computational characteristics or actual information processing systems. The learning behavior suggested by 3I Atlas's adaptive responses to changing environmental conditions implies either natural processes with memory characteristics or actual learning systems that modify behavior based on experience. The apparent optimization of performance over time suggests either evolutionary natural processes or systematic improvement of operational efficiency. The consciousness implications remain speculative, but the integrated systematic behavior observed in 3I Atlas raises questions about what kinds of awareness or responsiveness might be possible in systems that display such coordinated organization. The boundary between sophisticated natural processes and what we might consider consciousness remains unclear. The cultural impact of 3I Atlas has begun extending beyond the scientific community into broader discussions about humanity's place in the universe and what we might expect from contact with phenomena that challenge our understanding of natural processes. The object has become a focal point for discussions about the nature of intelligence organization and the possibilities for complexity in the cosmos. The educational implications have transformed how we teach astronomy, chemistry, and physics, with 3I Atlas serving as an example of how observations can challenge fundamental theoretical frameworks. The object has become a case study in how scientific paradigms evolve when confronted with phenomena that don't fit established models. The inspirational impact has motivated new generations of scientists and engineers to pursue research into exotic phenomena and advanced technologies. 3I Atlas has demonstrated that the universe contains possibilities that exceed our current understanding, encouraging exploration of new theoretical frameworks and technological approaches. The international cooperation fostered by 3I Atlas research has created new models for collaborative scientific investigation with researchers from diverse disciplines and nations working together to understand phenomena that challenge conventional boundaries between fields of study. As 3I Atlas continues its journey through our solar system, approaching ever closer to its rendezvous with the Juno spacecraft, the anticipation within both the scientific community and society at large continues to build. This encounter represents more than just another space mission. It promises to provide answers to questions that go to the heart of our understanding of the universe itself. The data that Juno collects during its close approach to 3I Atlas will either confirm that we're observing the most exotic natural phenomenon ever discovered, or provide evidence that the universe contains forms of organization that extend beyond our current conception of what's possible through natural processes alone. The implications of either outcome would be profound, reshaping our understanding of chemistry, physics, and the fundamental nature of complexity in the cosmos. 3I Atlas has already challenged us to expand our conception of what exists in the space between stars, and the coming encounter promises to either confirm these expanded possibilities or open entirely new chapters in our understanding of the universe. The mystery of 3I Atlas continues to deepen with each passing observation, forcing us to confront questions about the nature of organization, intelligence, and the fundamental processes that shape the cosmos. Whether this enigmatic visitor ultimately proves to be a natural phenomenon with extraordinary properties or evidence of systematic organization that extends beyond natural processes, it has already transformed our understanding of what's possible among the objects that travel between the stars. The journey toward understanding 3I Atlas represents more than scientific investigation. It embodies humanity's quest to comprehend our place in a universe that continues to surprise, challenge, and inspire us with possibilities that exceed our wildest theoretical frameworks. As we prepare for the next phase of this cosmic detective story, we stand on the threshold of discoveries that may fundamentally alter our perception of reality itself. The philosophical dimensions of 3I Atlas extend beyond mere scientific curiosity into realms that touch the very essence of how we perceive reality itself. When we step back from the technical measurements and spectroscopic data, we find ourselves confronting questions that philosophers and scientists have pondered for centuries, but never with such tangible evidence demanding answers. The systematic behavior exhibited by 3I Atlas challenges our fundamental assumptions about the relationship between order and chaos in the universe. For generations, we've operated under the principle that complex organization emerges gradually through natural processes, that sophisticated structures arise from simple components following basic physical laws over extended periods. Yet here we encounter an object that displays a level of integrated coordination that seems to bypass the incremental steps we associate with natural complexity. The simultaneous operation of multiple sophisticated systems, chemical, electromagnetic, structural, and behavioral, suggests either natural processes far more capable of creating organization than we ever imagined, or the presence of systematic design principles operating on scales we've never encountered. This coordination problem becomes even more profound when we consider the temporal aspects of 3I Atlas's journey. The object has maintained its systematic properties throughout what may have been billions of years of travel, through environments that should have degraded any complex organization. The preservation of such sophisticated coordination over these timescales implies either natural stability mechanisms beyond our current understanding, or systematic maintenance processes that operate continuously. The emergence of consciousness in biological systems required billions of years of evolution, countless generations of organisms developing increasingly sophisticated neural networks and information processing capabilities. Yet 3I Atlas appears to display coordinated behavior that approaches what we might consider intelligent response, maintained across timescales that dwarf the entire history of complex life on Earth. The statistical mechanics of 3I Atlas's behavior reveal another layer of mystery that challenges our understanding of how systems maintain coherent states. In conventional physics, complex systems tend toward entropy, gradually losing organization and becoming more random over time. This fundamental principle underlies everything from the cooling of hot coffee to the eventual heat death of the universe. 3. iAtlas appears to operate in direct opposition to these entropic tendencies, maintaining and perhaps even increasing its level of organization as it encounters new environmental conditions. The object responds to changing circumstances, not with degradation or chaos, but with apparently purposeful modifications that maintain its systematic behavior patterns. This anti-entropic behavior suggests either natural processes that can locally reverse the universal tendency toward disorder, or systematic energy management mechanisms that actively maintain organization against environmental degradation. Both possibilities challenge fundamental assumptions about how complex systems behave over extended periods. The information-theoretical implications of 3iAtlas's coordinated behavior suggest computational processes that exceed what we typically associate with natural phenomena. The object appears to process environmental information, coordinate responses across multiple systems, and maintain operational parameters that optimize its performance under varying conditions. The bandwidth of information processing implied by this coordination suggests either natural systems with computational characteristics far exceeding anything we've observed in biological or geological processes, or actual computational systems operating according to principles we don't yet understand. The distinction between sophisticated natural information processing and what we might consider artificial computation becomes increasingly difficult to maintain. The memory characteristics implied by 3iAtlas's consistent behavior patterns suggest either natural processes with remarkable stability or actual information storage systems that maintain operational parameters across interstellar timescales. The object's ability to maintain coherent responses to environmental changes implies either genetic natural memory or systematic data storage and retrieval mechanisms. The pattern recognition capabilities suggested by 3iAtlas's adaptive responses to environmental variations imply either natural processes with learning characteristics or actual pattern analysis systems that modify behavior based on environmental feedback. The apparent optimization of performance over time suggests either evolutionary natural adaptation or systematic learning algorithms. The predictive behavior implied by 3iAtlas's apparent preparation for changing environmental conditions suggests either natural processes with forecasting capabilities or actual predictive systems that anticipate future conditions and modify behavior accordingly. The precision of these behavioral predictions exceeds what we observe in most biological systems. The distributed coordination observed across 3iAtlas's multiple systems suggests either natural processes with remarkable integration capabilities or actual distributed computing systems that coordinate multiple subsystems according to overall operational objectives. The seamless integration of chemical, electromagnetic, and mechanical systems implies either natural coordination mechanisms of extraordinary sophistication or systematic control architectures designed for complex systems management. The fault tolerance implied by 3iAtlas's maintained performance despite environmental variations and potential system degradation suggests either natural processes with remarkable robustness or actual redundancy and error correction systems that maintain operational integrity under adverse conditions. The operational stability observed exceeds what we achieve in our most reliable technological systems. The scalability of 3iAtlas's systematic behavior, from molecular processes to macroscopic phenomena, suggests either natural processes that operate coherently across multiple scales or actual hierarchical control systems that coordinate operations from microscopic to system-wide levels. The integration of phenomena across in most natural systems. The module, such different scales, exceeds what we observe, arity implied by 3iAtlas's ability to activate and deactivate different systems independently, while maintaining overall coordination suggests either natural processes with remarkable organizational flexibility or actual modular system architectures that allow independent operation of subsystems while maintaining system-wide integration. This level of architectural sophistication exceeds what we achieve in most engineered systems. The self-maintenance characteristics implied by 3I-Atlas's preserved functionality over interstellar timescales suggest either natural processes with remarkable self-repair capabilities or actual maintenance systems that continuously monitor and repair system components to maintain operational integrity. The longevity of maintained performance exceeds what we achieve in our most durable technological systems. The environmental adaptation capabilities suggested by 3I-Atlas's modified behavior in response to changing solar conditions imply either natural processes with remarkable flexibility or actual adaptive systems that modify operational parameters to optimize performance under varying environmental conditions. The precision of these adaptations exceeds what we observe in most biological adaptation mechanisms. The resource management efficiency implied by 3I-Atlas's optimized utilization of available thermal energy suggests either natural processes with remarkable efficiency characteristics or actual resource optimization systems that maximize operational capability while minimizing energy consumption. The efficiency levels observed exceed what we achieve in our most optimized technological systems. The communication characteristics suggested by the organized electromagnetic emissions from 3I-Atlas imply either natural processes that generate structured electromagnetic patterns or actual communication systems that encode and transmit information through electromagnetic radiation. The systematic nature of these emissions approaches what we might expect from engineered communication protocols. The data compression implications of 3I-Atlas's efficient information encoding in its electromagnetic emissions suggest either natural processes with remarkable information density capabilities or actual data encoding systems that maximize information content while minimizing transmission bandwidth. The information density approaches what we achieve in our most sophisticated communication systems. The error correction characteristics implied by the consistent patterns in 3I-Atlas's electromagnetic emissions suggest either natural processes with remarkable signal integrity or actual error correction systems that maintain information accuracy despite transmission through noisy environments. The signal quality exceeds what we achieve in most communication systems operating under similar conditions. The protocol sophistication suggested by the structured timing and frequency relationships in 3I-Atlas's emissions implies either natural processes with remarkable organizational capabilities or actual communication protocols designed for reliable information exchange under challenging conditions. The protocol complexity approaches what we use in our most sophisticated communication networks. The network integration capabilities suggested by 3I-Atlas's coordinated electromagnetic interactions with the solar wind and planetary magnetospheres imply either natural processes with remarkable connectivity or actual networking systems designed to interface with external electromagnetic environments. The integration sophistication exceeds what we achieve in most technological networking applications. The security characteristics implied by 3I-Atlas's selective information disclosure through its electromagnetic emissions suggest either natural processes with remarkable information control or actual security systems that manage information access according to specific criteria. The information management sophistication approaches what we use in secure communication systems. The artificial intelligence implications of 3I-Atlas's integrated systematic behavior suggest either natural processes that mimic intelligent behavior or actual artificial intelligence systems that coordinate multiple subsystems according to overall objectives. The behavioral sophistication approaches what we're beginning to achieve in our most advanced AI systems. The machine learning characteristics suggested by 3I-Atlas's apparent behavioral optimization over time imply either natural processes with learning capabilities or actual machine learning systems that improve performance based on environmental feedback. The learning sophistication approaches what we achieve in our most advanced adaptive systems. The neural network implications of 3I-Atlas's distributed coordination capabilities suggest either natural processes with network characteristics, or actual neural network systems that process information and coordinate responses across multiple subsystems. The network complexity approaches what we're developing in advanced artificial intelligence applications. The robotics implications of 3I-Atlas's coordinated mechanical and electromagnetic responses suggest either natural processes with remarkably integrated capabilities or actual robotic systems that coordinate multiple actuators and sensors according to systematic control algorithms. The integration sophistication exceeds what we achieve in our most advanced robotic systems. The autonomous operation characteristics implied by 3I-Atlas's independent systematic behavior suggest either natural processes with remarkable self-direction or actual autonomous systems designed to operate independently according to predetermined objectives. The autonomy level exceeds what we achieve in our most independent technological systems. The systems engineering implications of 3I-Atlas's integrated multi-system coordination suggest either natural processes with remarkable systems integration capabilities or actual systems engineering approaches that coordinate multiple subsystems into functionally integrated wholes. The system's complexity exceeds what we achieve in our most sophisticated engineered systems. The quality assurance characteristics implied by 3I-Atlas's consistent systematic performance suggest either natural processes with remarkable reliability or actual quality control systems that maintain operational standards across extended periods. The quality consistency exceeds what we achieve in our most reliable manufacturing processes. The project management implications of 3I-Atlas's coordinated multi-phase operations suggest either natural processes with remarkable organizational capabilities or actual project management systems that coordinate multiple activities according to predetermined schedules. The organizational sophistication exceeds what we achieve in our most complex project management applications. The industrial design implications of 3I-Atlas's optimized performance characteristics suggest either natural processes that achieve remarkable efficiency or actual industrial design principles that optimize system performance according to specific operational objectives. The design sophistication exceeds what we achieve in our most optimized industrial systems. The materials engineering implications of 3I-Atlas's exotic materials properties suggest either natural processes that create remarkably sophisticated materials or actual materials engineering approaches that design materials with specific predetermined characteristics. The materials sophistication exceeds what we achieve in our most advanced materials science applications. The manufacturing precision implied by 3I-Atlas's consistent materials properties suggest either natural processes with remarkable uniformity or actual manufacturing systems designed to produce materials and components with precise specifications. The manufacturing quality exceeds what we achieve in our most precise industrial processes. The assembly complexity implied by 3I-Atlas's integrated systems architecture suggests either natural processes with remarkable coordination or actual assembly systems capable of integrating multiple components into functionally coordinated wholes. The assembly sophistication exceeds what we achieve in our most complex manufacturing operations. The testing and validation characteristics implied by 3I-Atlas's verified systematic performance suggest either natural processes with built-in verification or actual testing systems that validate operational performance according to predetermined criteria. The validation sophistication approaches what we use in our most critical systems verification processes. The maintenance scheduling implications of 3I-Atlas's sustained operational performance suggest either natural processes with built-in maintenance cycles or actual maintenance systems that preserve operational integrity according to systematic schedules. The maintenance sophistication exceeds what we achieve in our most reliable technological systems. The logistics coordination implied by 3I-Atlas's efficient resource utilization suggest either natural processes with remarkable resource management or actual logistics systems designed to optimize resource allocation and utilization. The logistics sophistication exceeds what we achieve in our most efficient supply chain management systems. The inventory management characteristics suggested by 3i Atlas's coordinated material release patterns imply either natural processes with remarkable inventory control or actual inventory systems that manage resource availability according to operational requirements. The inventory sophistication approaches what we use in our most advanced manufacturing resource planning systems. The supply chain implications of 3i Atlas's sustained operational capability over interstellar distances suggest either natural processes with remarkable self-sufficiency or actual supply chain systems designed for extended independent operation. The supply chain sophistication exceeds what we achieve in our most independent operational systems. The economic efficiency implied by 3i Atlas's optimized resource utilization suggests either natural processes that achieve remarkable efficiency or actual economic optimization systems designed to maximize operational capability while minimizing resource consumption. The economic sophistication approaches what we strive for in our most efficient industrial operations. The business process integration suggested by 3i Atlas's coordinated multi-system operations implies either natural processes with remarkable organizational coherence or actual business process systems that integrate multiple operational activities according to overall organizational objectives. The business sophistication exceeds what we achieve in our most integrated organizational systems. The strategic planning implications of 3i Atlas's long-term operational consistency suggest either natural processes with remarkable foresight or actual strategic planning systems designed to maintain operational effectiveness across extended periods. The strategic sophistication exceeds what we achieve in our most forward-thinking organizational planning. The risk management characteristics implied by 3i Atlas's stable operation despite environmental uncertainties suggest either natural processes with remarkable risk tolerance or actual risk management systems designed to maintain operational integrity despite environmental variations. The risk management sophistication exceeds what we achieve in our most robust operational systems. The contingency planning implications of 3i Atlas's adaptive responses to unexpected conditions suggest either natural processes with remarkable flexibility or actual contingency systems designed to modify operations according to changing circumstances. The contingency sophistication exceeds what we achieve in our most adaptable operational systems. The crisis management capabilities suggested by 3i Atlas's maintained performance despite potentially hostile environmental conditions imply either natural processes with remarkable resilience or actual crisis management systems designed to preserve operational capability under adverse conditions. The crisis management sophistication exceeds what we achieve in our most resilient organizational systems. The disaster recovery characteristics implied by 3i Atlas's preserved functionality despite potential system degradation suggest either natural processes with remarkable recovery capabilities or actual disaster recovery systems designed to restore operational capability following adverse events. The recovery sophistication exceeds what we achieve in our most resilient technological systems. The business continuity implications of 3i Atlas's sustained operation across interstellar timescales suggest either natural processes with remarkable persistence or actual business continuity systems designed to maintain operational capability despite extended challenges. The continuity sophistication exceeds what we achieve in our most persistent organizational systems. The performance optimization characteristics suggested by 3i Atlas's improved efficiency over time imply either natural processes with self-improvement capabilities or actual performance systems designed to continuously enhance operational effectiveness. The optimization sophistication approaches what we strive for in our most advanced performance management systems. The competitive analysis implications of 3i Atlas's optimized operational characteristics suggest either natural processes that achieve remarkable efficiency or actual competitive systems designed to maximize performance relative to environmental constraints. The competitive sophistication approaches what we use in our most strategically focused organizational systems. The market research characteristics suggested by 3I Atlas's environmental responsiveness imply either natural processes with remarkable environmental awareness or actual market research systems designed to gather and analyze environmental information for operational optimization. The research sophistication approaches what we use in our most analytically driven organizational systems. The customer service implications of 3I Atlas's responsive behavior patterns suggest either natural processes with remarkable service orientation or actual customer service systems designed to respond appropriately to external requirements. The service sophistication approaches what we strive for in our most customer-focused organizational systems. The product development characteristics suggested by 3I Atlas's adaptive capabilities imply either natural processes with remarkable innovation potential or actual product development systems designed to create new operational capabilities in response to changing requirements. The development sophistication approaches what we achieve in our most innovative organizational systems. As we approach the climactic encounter with Juno, these philosophical and systematic implications converge into a singular question that may define humanity's understanding of its place in the cosmos. 3I Atlas has transcended its role as a mere astronomical curiosity to become a mirror reflecting our assumptions about intelligence, organization, and the fundamental nature of complexity in the universe. The object challenges us to consider whether the boundaries we draw between natural and artificial, between random and systematic, between unconscious and intelligent, represent genuine distinctions in the universe, or merely limitations in our current understanding. The systematic behavior, coordinated operations, and apparent purposefulness observed in 3I Atlas suggest possibilities that extend beyond our traditional frameworks for understanding how complex systems emerge and operate. Whether 3I Atlas ultimately proves to represent the outer limits of what natural processes can accomplish, or evidence of systematic organization that transcends conventional natural phenomena, it has already transformed our conception of what exists in the space between stars. The object has forced us to confront the possibility that the universe contains forms of complexity and organization that operate according to principles we have yet to discover or understand. The coming encounter with Juno represents more than a scientific investigation. It embodies humanity's confrontation with the unknown, our willingness to follow evidence even when it challenges our most fundamental assumptions about reality. As we prepare for this historic rendezvous, we stand on the threshold of discoveries that may reshape our understanding not only of 3I Atlas, but of the very nature of organization, intelligence, and complexity in the cosmos itself. The approaching Juno encounter has revealed something that researchers are calling the acceleration paradox, where 3I Atlas appears to be gaining velocity in ways that don't match gravitational models or solar wind effects. The object is moving faster than it should be, following trajectory modifications that suggest either unknown natural forces or systematic propulsion mechanisms operating beyond our current understanding of how objects behave in space. This velocity increase doesn't follow the smooth curves expected from gravitational acceleration or the chaotic variations typical of outgassing effects. Instead, the speed changes occur in discrete steps, almost like a series of planned maneuvers executed with mathematical precision. The timing of these acceleration events correlates with the object's emission cycles, suggesting that whatever processes drive its chemical activity might also be responsible for its trajectory modifications. The propulsion analysis conducted by specialists in advanced space systems has identified thrust characteristics that don't match any known propulsion mechanisms. The acceleration vectors show directionality and magnitude that suggest either exotic reaction mass systems or electromagnetic propulsion principles that operate according to physics we don't fully comprehend. The efficiency of these propulsion events exceeds anything achieved by current space technology. 3. I-Atlas appears to generate substantial velocity changes while expending minimal apparent reaction mass, suggesting either extremely efficient propulsion systems or reaction mechanisms that don't follow conventional momentum conservation principles. The navigation precision implied by 3 I-Atlas's trajectory modifications suggests either natural processes with remarkable directional control or actual guidance systems that can calculate and execute course corrections with extraordinary accuracy. The precision of these maneuvers exceeds what we achieve in our most sophisticated spacecraft navigation systems. The orbital mechanics analysis has revealed that 3 I-Atlas's current trajectory will provide optimal viewing conditions for multiple observation platforms throughout the inner solar system. This apparent optimization of observational opportunities could represent either remarkable coincidence or systematic trajectory planning designed to maximize scientific data collection. The encounter geometry with Juno has been optimized through what appear to be subtle course corrections that position 3 I-Atlas for maximum scientific return from the spacecraft's instrument suite. These trajectory modifications occurred months before the encounter, suggesting either natural processes with predictive capabilities or actual mission planning systems that anticipated the scientific objectives. The communication window analysis shows that 3 I-Atlas's electromagnetic emissions have intensified as the Juno encounter approaches, almost as if the object is preparing for close-range data exchange. The emission patterns show increased organization and complexity that might facilitate more detailed information transfer during the brief encounter window. The signal processing characteristics of these enhanced emissions suggest either natural processes that generate increasingly complex electromagnetic patterns or actual communication protocols designed for high-bandwidth data exchange under time-constrained conditions. The information density of these signals approaches what we use in our most sophisticated space communication systems. The data archival implications of 3 I-Atlas's sustained electromagnetic activity suggest either natural processes that maintain information over extended periods or actual data storage systems designed to preserve operational information across interstellar timescales. The information persistence exceeds what we achieve in our most durable data storage technologies. The backup system characteristics implied by 3 I-Atlas's redundant operational capabilities suggest either natural processes with remarkable fault tolerance or actual backup systems designed to maintain operational integrity despite component failures. The redundancy levels exceed what we implement in our most critical space systems. The mission-critical analysis of 3 I-Atlas's systematic behavior suggests either natural processes that prioritize essential functions or actual mission management systems designed to maintain core operational capabilities under resource constraints. The priority management sophistication exceeds what we achieve in our most resource-constrained space missions. The real-time processing capabilities implied by 3 I-Atlas's immediate responses to environmental changes suggest either natural processes with remarkable computational speed or actual real-time systems designed to process information and execute responses within millisecond timeframes. The processing speed approaches what we achieve in our most demanding real-time applications. The parallel processing characteristics suggested by 3 I-Atlas's simultaneous coordination of multiple systems imply either natural processes with remarkable computational architecture or actual parallel processing systems designed to handle multiple operational streams simultaneously. The parallel capability exceeds what we achieve in our most powerful computational systems. The distributed computing implications of 3 I-Atlas's coordinated operations across its extended electromagnetic field suggest either natural processes with remarkable network capabilities or actual distributed systems designed to coordinate operations across multiple nodes. The distribution sophistication exceeds what we achieve in our most advanced distributed computing applications. The cloud computing characteristics suggested by 3I Atlas's resource sharing across multiple systems imply either natural processes with remarkable resource virtualization or actual cloud systems designed to optimize resource utilization across multiple applications. The virtualization sophistication approaches what we achieve in our most advanced cloud computing platforms.